So now you can go live. The blue thing is there. You can इसको minimize कर दो. It's like.
But where is the other screen?
This is the screen.
No, I know, but the participants वाला screen.
इसको छोटा कर दो. Screen. ये.
Yeah. Okay, so there it is. इसको छोटा करना है.
Just wait. I'll just do it. Yeah. Oh, you are not a Mac person.
I'm not a Mac person. No.
Too bad.
I'm an iPad person, but not a Mac.
Yeah, no, you have to change your allegiance completely.
No, I don't want to go to the dark side.
You don't know the power. All right. Okay, you're all set. It is also open for.
Yeah, maybe that announcement we can make.
So
yeah, go ahead.
How many of you? So again, we'll announce it now, and at the end of the so just to let you know, so we had this discussion on the meeting scheduled after lunch, but since we don't have any other talks after lunch, the plan is to do it immediately after the last talk, which is around 12:30, so that by 1:30 we can wrap up the meeting. So that is the change. I have sent an email out to that effect. Yeah, so that's the announcement. We'll just, once more participants come at the end of the session, maybe Ravi, you can announce it once.
Yeah. Okay, Amit, you can go ahead and share it again. I think.
Yeah, just a minute. Okay.
Okay, no, just 1 second. Arijit is here.
Let's check his then.
Yeah, we'll just check Arijit's. Then we can. So Arijit, I've made you a co-host. Just share your screen. Arijit?
So is this going to be my talk?
No. We just want to make sure that your screen sharing, etc., is working fine, and then we'll start with the next talk. Yeah.
Yeah, it is.
I think you can see all your emails.
Yeah, you can see my emails.
No, the presentation. Just share your presentation so that maybe.
Okay.
We don't want to read your email. Come on.
Yeah, this should be it.
Yeah. Okay, take it. It's fine. So just unshare, then Amit can start his talk.
Share again.
You have to mute yourself.
I have to, yeah. Yeah, Amit, go ahead.
Yeah, I'll just start. Just give me a minute.
Yeah. So 20 plus 5. Yeah. Okay, so welcome formally to all of you to the morning session today, and we have Amit Agarwal, Bhaskaran Madhukaran, and Arijit Kundu and Gaur Jana as our speakers. And first talk is by Amit Agarwal from IIT Kanpur, and he'll tell us about novel magnetotransport and Hall effect in quantum materials. So Amit, I'll tell you when you finish 19 minutes so that you have some time for questions.
Sure. I hope you won't need to. Okay. So first of all, let me thank all the organizers for organizing this young investigators meet. I always feel younger when I'm talking in this, actually. Okay, so for that, a big thumbs up. And then, so a lot of younger colleagues may not know, Ravi and myself have the same PhD guide, and we used to share the same office during our PhD, or at least during my PhD, let's say. So, it's a pleasure to talk in the same session in which Ravi is the chair. Okay. With that out of the way, let's go ahead. So I took the liberty of modifying my title a bit, but I'll still talk about magnetotransport. Okay. But the talk will primarily be focused on geometric properties of the electronic wave function, and particularly how that geometric property will manifest in transport of electrons in crystals, basically. And in particular, I'll talk about one work, which is this titled as orbital magnetic moment induced intrinsic Hall effect. Okay, so intrinsic meaning which doesn't have the scattering time scale involved in it, so it is also dissipationless and also a bit of purely quantum mechanical origin, actually, with no classical analog. Okay, and most of this work was done by this student Kamal, who's in this striped t-shirt towards the left. Okay, and yeah, this is a picture from last year when times were better. Okay, okay, so let's proceed. So the story starts from very let's say basics, like the electron wave packet in crystals can have translational or rotational motion, and in crystals with block dynamics, etc., these two motions can combine to give you geometrical properties, which we will call Berry curvature and the orbital magnetic moment. Okay, and these two are finite only in systems which have broken inversion symmetry or broken time reversal symmetry, or both can be broken, etc. But we will just deal with either of these two symmetries is broken. And the main idea is that this Berry curvature and the orbital magnetic moment, they couple to external perturbations, magnetic field, electric field, temperature gradient, etc., in interesting ways. And this gives rise to new kind of transport phenomena in, let's say, transport experiments and also in optical experiments. Since it couples to the external electric field and magnetic field, so light waves also can couple to these, and they give new kind of phenomena in optical experiments. Okay, and predominantly I'll talk about this intrinsic Hall conductivity induced by this orbital magnetic moment. So one of these geometric properties, and this we just very recently, I think yesterday, it appeared on arXiv, this paper. Okay, so more details can be found here. Okay, okay, so let's go. So in general, geometric properties of the electron wave function happens to be one of the most interesting ideas in quantum mechanics, and it particularly became prominent around 1984, when all the work on so the Berry's curvature paper came out, and all the work following that on quantum Hall effect, etc., was written in terms of Berry curvature and so on. Okay, and roughly, so this is still one of the most interesting ideas in quantum mechanics, which arose after almost 57, 60 years after the discovery of quantum mechanics, let's say. Okay, and for younger colleagues, this idea is simple, that wave function moving around in the Brillouin zone, let's say kx and ky. So I have a 2D representation in this central figure. It generates a irreducible phase, which is called the Berry phase. Okay, and the Berry phase can be written in terms of integral of a quantity times the, let's say, the normal wave vector out of the area, which I encircled. So in this case, out of the plane vector, let's say. Okay, and this is very similar to the way we write magnetic flux going out of a system in real space, let's say. So the magnetic flux I'll write as B dot N dx dy, and the Berry curvature you will find can be written in terms of this quantity omega, which I'll call Berry curvature and dx dy. Okay, and this Berry curvature, just like the magnetic field in the magnetic flux, acts like a magnetic field, but in the reciprocal space or in the momentum space, let's say. Okay, okay. While magnetic field acts in the real space. So this is an analogy which helps us think of the Berry curvature in terms of magnetic field in the momentum space. But this is analogy at best, and should be stopped there. Okay, and okay. Now it turns out when you do this analyze materials really, etc., so this Berry curvature will be connected to degenerate band crossings points or band inversions, etc., and also to orbital magnetization in the Brillouin zone, actually. Okay, and similar to the magnetic field, which is connected to magnetic monopoles and circulating currents in the real space. So those kind of charges can generate a magnetic field. Similarly, Berry curvature can be generated by or is related to band crossings and so on. Okay. And of course, I already said that this gives rise to very interesting geometrical phenomena in quantum materials. So some of these I'll highlight below. So for example, the Berry curvature is actually a curvature in the Brillouin zone or the reciprocal space. And this gives rise to almost all topological properties of materials. Okay. In fact, all the topological indexes I can possibly write in terms of the Berry curvature alone, and so on. They are related to the exotic surface states which appear, which is the one of the most important physical consequence of topology in materials, let's say. Okay. In addition to this, we will see that this gives rise to an additional velocity for the electron motion in crystals, which comes as E cross omega. So this is the coupling of the electric field to a geometric property of the electronic wave function. It modifies the equation of motion and gives rise to novel transport phenomena. Similarly, I have another property, which is the orbital magnetization, which comes from the self-rotation of the block wave function, etc. That couples to, Valley polarization. So Valley Hall effect that can give rise to Valley Hall effect or nonlinear optical effects. And it also manifests in transport, actually. So the transport manifestation of orbital magnetization and anomalous velocity in transport is what I will focus on in this talk. Okay, so this is just to give you a broad overview of, for us in our group, what are the current excitements and what are the future directions which we'll pursue or which we are excited about, let's say. So current excitements are, the connection to the topology, symmetry properties of, which kind of symmetry in materials, crystalline symmetries will give rise to which kind of effects. So the equation of motion going beyond linear order, let's say higher order responses, etc. In terms of transport, quantum anomalies, Hall effects, different kinds of Hall effects. Then theoretical framework for, treating all the different components of charge transport in a consistent way. Etc. Then in optics and plasmons, so optical Valley Hall effect, linear optical effects, Faraday rotation, etc., and so on. And future directions is mostly about, so some fundamental questions related to how the Berry curvature enables the surface states, what are the very precise criteria for their existence, and more recently just started thinking about fractional topological charge, so the ideas are not clear there. And nonlinear transport, and in terms of optics, higher harmonic generation, shift current for photovoltaic efficiency, new kind of electromagnetic coupling which arises in magnetic topological insulators, which is generally termed as axion electrodynamics, etc., and so on. Okay, so with that out of way, let's go to we'll talk about primarily magnitude transport. And since we will be using this coupling of Berry curvature and orbital magnetic moment, so let's see how this arises, etc. So given let's say a Hamiltonian, arbitrary Hamiltonian H, these formulas list how I can calculate the band resolved Berry curvature and orbital magnetic moment. Okay, so the sum over n prime is missing here, so n prime is the other band, so I should sum over all the other bands. Okay, and just connected to, let's say, the velocity matrix elements with combinations of energy. Okay, so that's the orbital magnetic moment, and this is the Berry curvature. Okay, and the major impact of these two quantities is, let's say, it impacts the electronic band structure. Okay, so the electronic bands xi k, let's say, which will be the eigenvalues of H, change by a Zeeman-like coupling, where orbital magnetic moment couples to the magnetic field, external magnetic field, if it is present, basically. Okay, and this also modifies the band velocity. So band velocity gets an additional term, which is the derivative of mk dot b. Okay. Okay, so this is one impact on the electronic bands, and this is why the orbital magnetic moment gives rise to Valley polarization. So it can, so between the different values of graphene, M has opposite signs, and it gives rise to shifting of bands between the two valleys, which is called Valley polarization. Okay, very important to observe Valley Hall effect and so on. Okay, okay, so this is one. And then in addition to the band structure effects, it also changes the dynamics of electrons in crystals. Okay, so if you do a simple perturbation theory calculation, you can show that to lowest order in the electric field, you get this kind of correction. So R dot, which naturally is basically the first expression, the band velocity minus k dot cross omega, and in hk dot, I get this Lorentz force term, just that the velocity is modified to the include the orbital magnetization correction now. Okay, but these two equations are coupled. If you decouple them, Then we start getting more complicated equations with lots of terms in r dot and k dot. Okay, and these were shown in an earlier talk also. So I'll just highlight some important physics which comes out of these. Okay, so this is how Berry curvature and orbital magnetic moment leads to novel transport. Let's say. So this is the r dot equation. So the velocity equation. Okay, so I have the band velocity. Let's say. In addition, I get this additional velocity term, which I'll call the anomalous velocity. And it is called anomalous velocity because of it gives rise to what is called anomalous Hall effect. So a Hall effect in the absence of a magnetic field. Okay, the intrinsic component of that is just directly proportional to the anomalous velocity. Then there's this extra term where the Berry curvature couples to the magnetic field. Okay, and this gives rise to a velocity component which is parallel to B. Okay, and this is called the chiral magnetic velocity, and it gives rise to chiral magnetic effect, which was experimentally observed few years back. Okay, I think in ZRSIS. Okay, okay, so this is the velocity terms, and all of these are accompanied by a prefactor dk, which also includes the magnetic field coupled to the Berry curvature. So this also has some impact, but I'll not focus here. Okay, and k dot is hk dot is the force, let's say, acting on the block electrons. So I have the Lorentz force in presence of external fields, plus I get this extra term which has a electromagnetic coupling. So E dot B times omega k. Okay, so this I'll just call Berry force. Okay, and this is a magneto. This gives rise to magneto-electric coupling. So in, let's say, condensed matter systems, axion electromagnetic kind of effects, let's say, negative MR. So it can give rise to negative MR. Okay, it can give rise to planar Hall effect, and it also gives rise to chiral anomaly-like physics. So I say chiral anomaly-like physics because these are very general. So I have not specified a material, etc. So I may not have a chiral charge in the system, but this term may still be there. Okay, so without having a chiral charge imbalance, which is associated with the chiral anomaly, let's say, strictly speaking, I can still have this kind of an effect, which looks like mimics chiral anomaly effect. And this, for example, has been shown to give rise to negative MR in even in topological insulators, for example, which doesn't have any chiral charge and so on. Okay, so this already gives you an idea probably that, you know, there are a lot of exotic and novel magnetotransport effects which can arise because of this coupling of the geometric properties of the electron to external fields. Okay, okay, so we also had some work related to, you know, exploration of these Berry curvature and orbital magnetic moment induced transport phenomena. So some of these Kamal talked about, etc. So predominantly some work on chiral anomalies was done this year with Kamal and another student, Shahil, who's currently in ICTS as a PhD student. Okay. Okay, so I'll not discuss this. In addition to this, there's another work on Magnus Hall effect. So another of my student, Devuttam, will talk about it in the other session. Okay, so this was more or less my overview of the field. And now let's move to more specific details of intrinsic Hall conductivities induced by this orbital magnetic moment. Okay, so the simple idea, just to understand this very clearly, so we have a Lorentz force V cross B, let's say, that gives rise to classical Hall effect. Okay, and the classical Hall effect happens to be an extrinsic effect. It actually depends on the impurity scattering. It cannot exist if there are no impurities in the system. Then I have the anomalous velocity, which gives rise to anomalous Hall effect, which is intrinsic in nature. And I have this orbital magnetic moment, which modifies the band dispersion plus the anomalous velocity. The combination of these will give rise to this new orbital magnetic moment induced Hall effect, which is sort of intrinsic in nature. Okay, so calculation or the framework to calculate this, let's start from a semi-classical equation of motion for the Hall configuration. E, B are perpendicular to each other. So this equation of motion I already showed you earlier. Okay, yeah, and then in addition to the r dot, let's say the actual physical velocity of the electrons, I'll need the distribution, non-equilibrium distribution function. So we will adopt the simplest formalism, let's say the Boltzmann transport equation for doing this within the relaxation time approximation. So I make it even simpler basically. So I'll not worry about collision integral details coming from more exotic scattering terms, etc. Okay, and just to make it more simpler, I'll also assume that the tau doesn't have any energy dependence, etc. But you can include that, and it will not change any of these results qualitatively at all. Okay, okay. Now, in presence of all of these terms, so in this equation, I'll feed in r dot and k dot. Okay, and I can do a systematic calculation for the non-equilibrium distribution function. Let's say to linear response in the linear response regime, linear in electric field and linear in the magnetic field, I'll get these many terms basically, okay, which include these couplings, double derivative of the Fermi function, single derivative of the Fermi function, the scattering time scale tau, and so on. Okay, and now I have the distribution function, I have the velocity, I can calculate the currents.
Amit, you have 4 minutes.
Okay, and having obtained the current, I can obtain the conductivities, let's say. Okay, so that's the idea. Okay, so I use this framework and I actually calculate, let's say, just to check that I'm doing everything consistently, I'll check the Lorentz Hall conductivities first, basically, and that from that framework, this expression is what will come out. And now you can use this and go ahead to calculate this for, let's say, parabolic dispersion system, for graphene, for anything, etc. And we find that it gives consistent results. Okay, from the same framework, you will get this orbital magnetic moment induced Hall conductivities. So sigma, alpha, alpha bar, and kappa. And you get this epsilon m, which is the m dot b. So the magnetic field induced correction times the Berry curvature times the derivative of the Fermi function, basically. So these are the new orbital magnetic moment induced Hall conductivities. In this expression, you see there is no tau. So these are sort of intrinsic. Okay. And in addition, there will be also a lot of corrections in the longitudinal conductivities induced by both Lorentz term, the Berry curvature, and the orbital magnetic moment, which I am not writing the expressions for. Okay. And a simple way to understand this is, if you look at the expression of the anomalous Hall effect, I have this expression, okay, where the Berry curvature is integrated over the Fermi C. Okay, and now in the Fermi C, I make this transformation, so I can write the Fermi function as the Fermi function of epsilon. So that gives me the anomalous contribution plus derivative of the Fermi function times this m dot b. Right. So that is precisely what gives rise to this orbital magnetic moment induced Hall effect. Okay. Now, a quick symmetry analysis will tell us that the Berry curvature and the orbital magnetic moment are odd under time reversal symmetry and even under inversion asymmetry. Okay, so if you put in these equations, etc., you'll find that if my system is intrinsically time reversal symmetry broken while inversion symmetric, then the only intrinsic contributions I will get are basically this OM induced and the anomalous Hall effect, actually. And extrinsic Hall, I'll get the Lorentz contribution plus a lot of other contributions arising from this geometric terms, which are extrinsic. Okay, and if the system is intrinsically time reversal symmetry preserving but inversion symmetry broken, then I'll get this OM induced intrinsic Hall. That's the only intrinsic Hall effect, and the only extrinsic Hall effect is the Lorentz force induced extrinsic Hall effect. So all other effects sort of vanish. Okay, so this is where we will focus in the rest of the talk, and I'll particularly take two systems. So 2D, let's say gapped graphene with two distinct valleys and inversion symmetry broken Weil-Say metal, which has 4 nodes in the Brillouin zone. So you can calculate all of these coefficients and tabulate, etc. So let's not discuss, but yeah. So just showing you results for gap graphene, for example, this is the Hall conductivity. So sigma xy, and delta G is the band gap, which I can induce in graphene placed on boron nitride, let's say. So delta G is 26 MeV taken from an experiment, which showed the Valley Hall effect for the first time. So you see that the orbital magnetic moment induced Hall conductivity can be larger than the Lorentz Hall conductivity near the band edge. Okay, and this is expected because the band crossing points and the band inversions are the hotspots of the Berry curvature and the orbital magnetic moment, and thus these geometric effects are dominant near the band edges or band crossings, actually. Okay, okay, and one immediate implication of this is that the Hall conductivity we use to estimate the charge carrier density in materials, basically, right? And that comes from the simple relation that if I calculate this rho xy, let's say from the Lorentz, then I can show that it is B by NE. even for a gap graphene system, even for a wild semi-metal. And that allows us to calculate this Ne as the 1/8 times the Hall number, where the Hall number is defined as this derivative of rho xy as b goes to 0. Okay.
So Amit,
And
you
now,
should try to wrap up probably.
yeah, I'll take a minute. Okay. And sigma xy now has an extra contribution. So you get this extra R sigma contribution. And because of that, you get this extra density contribution basically. So if I use the conventional formula, I should get a density of, let's say, 25 here. But if you include orbital magnetic moment contribution, you can get a the density of 35, let's say. So it's quite significant near the band edges. It will also have some impact on the MR. So it can induce, so the normal Lorentz hole doesn't induce any MR, negative MR or any MR actually, but the orbital magnetic moment can induce MR, and that brings us to the summary. Okay. So the orbital magnetic moment induces a new intrinsic Hall effect, which is linear in the magnetic field. In inversion symmetry broken system, there is the only intrinsic Hall response. In TRS broken systems, the anomalous Hall effect and other extrinsic geometric Hall responses will be there along with this, and difficult to distinguish. It leads to carrier density underestimation in Hall experiments, and it also leads to negative MR, which is quadratic in the magnetic field. So I should stop here and let's take some questions.
Thank you, Amit. So we have a couple of minutes, 3 minutes for some questions if people have any. Yes, I can ask a question. So Amit, you did this for, you said the graphene hexagonal lattice, is this? The calculations that were done for? Okay.
Yeah.
Do you expect any dependence on lattice structures, in the sense that if it is not bipartite and things like that?
No, sure. So the details of the how the orbital magnetic moment varies, etc., depend on the crystal lattice, etc., right?
Yeah.
Just that I should have a Berry curvature and the orbital magnetic moment in the system. So I need systems which are either intrinsically time reversal symmetry broken or inversion symmetry broken.
What happens if both are broken?
So I can have a Berry curvature, but then so then the analysis is more complicated. Yeah. So So if both are broken, then I'll have this more complicated terms also. So so what I'm saying is there are other terms, geometrical terms, which are extrinsic in nature, right? But experiments do not care about extrinsic, intrinsic. It will just measure the total. So it will be difficult to distinguish, let's say, or highlight these effects.
Okay.
Okay.
Okay. So let me just check if there are anything. Okay. So there are no further questions. So let's thank Amit for the nice talk and move on to the next speaker. So thank you, Amit. So if you could unshare your screen.
Yeah, I'll just stop sharing my screen. Okay. Thanks.
Bhaskaran? Yeah. Okay, our next speaker is Bhaskaran Muralidharan from IIT Bombay, Department of Electrical Engineering, and he's going to tell us about Majorana conductance quantization. Yeah, you can go ahead. I'll warn you when you have 2-3 minutes left out of your 20, so that you know. Okay. Can you hear me, Bhaskaran?
Sorry, I had to unmute myself. Yeah, now you can hear me, right?
Yeah, I can hear you. So you can go ahead. I'll warn you when you have 2 or 3 minutes left. Okay?
Yeah. 1 minute. Yeah, I'll start now. Okay. Thank you.
Yeah, go ahead. Yeah.
All right. Thank you very much for giving me a chance to speak here. I was here last year too, and this is kind of a continuation of what I was doing. So I'm in the Department of Electrical Engineering, and I'm going to talk a lot about this Majorana conductance quantization signatures, which are quite a topic of great interest these days. So very quickly, let me give you some background. The thing is, the Rashba nanowire system is by now very popular, and it is one of the leading platforms to host the Majorana zero modes, right? And due to this fact, there is lots of research going on in this field. Okay, one of the most important thing is the most recent setups include the fact that you have this Majorana, I mean, you have the Rashba nanowire, and you're coupling that to sort of superconductors, and then you create the topological superconductor, and most of the measurements are done on the systems that include two contacts, that is source, drain, and the topological superconductor. One of the most important things we have to consider now is the fact that there is an Andreev reflection process that kind of determines the quantization of conductance. And the current controversy today is the fact that whether you have actually seen a Majorana or not. And so I'll have to take a minute, excuse me for this, but I have to arrange for a pointer. And I'm sorry I didn't get that done. Okay, I think, sorry, I have to take a minute for that. Okay, so now could you see my pointer, or there's no pointer yet?
No, I don't see it at the moment.
I actually.
Actually, it was okay with just the cursor. I mean, do you actually need the pointer to change?
Oh, you could see my cursor. I couldn't see it myself.
No. Yeah, we can see the
Okay.
cursor. Yeah.
Okay, and so the current controversy is whether we found a Majorana state or it's some sort of a false positive. Okay, given that fact, I'll be talking a little about it. And of course, the aim is to create these topological quantum computers. Once you find these, once you ascertain the fact that they are Majoranas, the next job for device engineers is to figure out how to exchange them, fuse them, etc., which is on the right panel. We talk about topological QC operations. So let me just quickly give you an update of the experiments. So the basic idea is at the interface between the topological superconductor, right, on the left panel, and the contact, which is a normal metal, is a process called Andreev reflection, where basically the electron enters the system and it becomes a Cooper pair inside the superconductor and it sort of emits a hole, creating the famous conductance doubling. However, when a zero mode exists, which is supposed to be the telltale signature of the Majorana, what's going to happen is you're going to see a perfect quantization of the conductance, the 2e square by h. And that was some sort of a telltale signature people talked about. However, there are lots of controversies in this, but today I'm going to talk about mainly the transport simulations of such signatures. Okay, so the latest update is that the very good experimental facilities have resulted in almost a quantization of conductance. Okay, and very importantly, why electrical engineering work involves this stuff is because all of these depend on the existence of the edge states in the left and right, at the interface, and so we have to include contacts, and all experiments are based on conductance measurements, which is basically current voltage characteristics and the derivative. Okay, so my talk is basically, I'll just introduce this based on a few of our works of late in the last few years, and on the right panel, and these are called the superconducting hybrid systems, etc. And I'll be introducing you the Kitaev model very briefly, and then I'll talk about the Keldysh non-equilibrium Green's function technique, which is one of the techniques of quantum transport modeling. Professor Amit talked about Boltzmann, which is another technique. Then I'll talk about the Rashba calculations, and of course, the more important thing of today's talk is the inclusion of dephasing interactions into the Majorana zero mode. Okay, very super crash course of superconductivity, because many people do not know this too well. So we start with the BCS Hamiltonian that sort of pairs only momenta of opposite directions, and that's because of certain Fermi sphere arguments presented by Cooper. Then we introduce the mean field theory, and ultimately at the end of the mean field theory, what we see is you get the on-site term, that's epsilon k there, and then you get the term that is a Coulomb interaction term. And the regular Coulomb interaction terms that you know of is C dagger C, which is the the Poisson term. The Poisson term kind of goes into the on-site energy, and you get these two nice terms, that is the CK and CK dagger, which are the pairing terms, that is the extra superconductivity terms. And with that, we can write the mean field Hamiltonian from the BCS model as something like the on-site energies plus the pairing term delta times C dagger and delta star times CC. Now you could do a simple mathematical trick called the electron hole transformations. You could keep the upspin as it is and make the downspin a hole transformation. And by doing that, you get something called the Bogoliubov-Dijon's form. And what happens is, you all know that, when you have a normal metal, you have the upspin band and the downspin band filled up to the chemical potential mu, the parabolic bands. And when you do this electron hole transformation, the upspin band remains as it is, but the downspin band is flipped over and brought up. And so you get this kind of a spectrum on the lower panel. And so you get the Hamiltonian of the first quantized Bogoliubov-Dijon, which is basically epsilon minus mu, which is the upspin band, and epsilon minus of epsilon minus mu, that's the hole, and then the pairing potential being the off-diagonal term. And if you want to write in second quantized notation, you have this wave function. The field operator psi is not a spinor anymore, but it's called a Nambu spinor, which has the electron part and the hole part, which is the dagger of the electron part. So when we have, so based on that, you could get something called an excitation spectrum, and basically you have, the bands like follow this part. So the metal can be represented on the left panel as the excitation spectrum like this, and so there's an electron part and the hole part, right? And at the interface, so with the superconductor, there is a gap induced by the off-diagonal terms, and so you have this type of a system. And so at the interface of electron and at the interface of the normal and superconductor, you have this, unrave reflection. One more thing I'd like to remind you, you can diagonalize the Bogoliubov-Dijon Hamiltonian using these Bogoliubov operators, which can be written as a superposition of the electron and the hole components. Okay. Now, based on this, something interesting came up, which is, can we have, you see the Bogoliubov quasi-particle is a superposition of electron and a hole. As you can see, gamma is equal to UC dagger plus BC. Now, you could have a condition where a mid-gap excitation, right, as Majorana at some point came up with this idea. So the mid-gap excitation could satisfy gamma dagger is equal to gamma, which is the most fun stuff. And so it turns out that you cannot do it so easily with a spinful system, but you could do it with a spinless system. And so no wonder Kitaev's first model is a spinless model of the, such an excitation. That is the famous condensed matter version of the Majorana fermion, which was proposed by Majorana before he mysteriously disappeared in 1930s. Okay, so for introducing the Kitaev model, we go into the real space. And in real space, you could write a superconducting Hamiltonian as a regular tight binding matrix, tight binding Hamiltonian, with the on-site and off hopping terms. And then you have the extra pairing terms. Now, when you have a S-wave superconductor, the pairing is on each side, the up and down can pair. But you want a spinless model, so you cannot pair on the same side, right? You do exclusion. So therefore, you want to pair neighboring sites, it becomes a so-called P-wave model, and that's the 0th model of the topological superconductivity introduced by Kitaev. So you can have pairing between site 1 and site 2, site 2, site 3, so on and so forth, represented by this Hamiltonian downstairs. And then you do some interesting transformations, which is basically converting it into equal excitations of electrons and holes, and writing two operators and rewriting the Hamiltonian, you get something like this. And this is the famous Kitaev Hamiltonian that is based on the Majorana operators. So the above basis, the first basis is the real site basis. The down basis is the Majorana basis, okay? And of course, under specific conditions, this looks like a SSH chain that is paired. So under specific conditions, you have a generic model, then you have a trivial chain when delta is equal to T, and then you have a topological chain when delta is equal to T and mu is equal to 0. And this is the famous existence of the 0 modes at the two sides. Gamma 1A and gamma Bn remain at the edges. And this is the famous paper of Kitaev. And of course, this is just the simple model. And if you actually go into momentum space, you will get the topological phase space of the Majorana 0 modes. That is when mu is greater than, this is a space of mu by delta and T by delta. And you can see the shaded regions are the regions where the winding number exists, which is also for 1D models, a winding number or Jack phase is typically used to represent the topological identity. And so you can see that there is a region in phase space that's topological, well known from the Kitaev model in momentum space. However, we'd like to move on now to the topological properties of a finite Kitaev chain. And so one of the most interesting thing is if we look at the phase diagram, let's say the first quadrant of the phase diagram, in the infinite, thermodynamic limit, you will see Majorana should exist in that whole blue region. However, if you go into the discrete region, a discrete chain, let's say n is equal to 20, you will see that the Majorana modes, exact zero modes, only exist along these sort of fingers, along these lines. And this we call as Majorana lines. And what you would expect naively is that if you actually scan that phase space, you will get the Majorana conductance peak only along these lines. Okay, so these are the lines for n is equal to 20 and n is equal to 100, as you can see on the right panel. So with this, we move on to transport, because finally, I'd like to give you two more insights. When you put two contacts, the normal metals, to this topological superconducting channel, what happens is we'll first now introduce a Keldysh formalism. And before we even get there, I'd like to remind you that the Majorana zero mode is beautifully, can be sort of at least diagnosed by this so-called Andreev reflection process that happens at the interface. Now, the other thing is that in the Bogoliubov-Dijen representation, if you have a superconducting channel, then the metallic channel comprises of two contacts, that is the electron part and the hole part. And so the Andreev reflection is basically a local reflection between the electron and the hole. And then you have non-local conductances, that is the direct transmission that takes you from the electron on the left to the electron on the right, and the crossed Andreev process that takes you from the electron on the left to the hole on the right. So this is basically the Landauer-Buetiker way of looking at things. So what we need is this 2e square by h conductance quantization of the Majorana zero mode, which is caused by the pure Andreev reflection at the local end. Okay, so let's move on. So again, I remind you of the experiments. The right panel especially is the experiment by, again, Cowenhoven's group. Some controversy there still about the quantization, but he does see a neat quantization as he changes the magnetic field of the system, which I'll get into now. Okay, so let me move on to the Keldysh non-equilibrium Green's function technique. So we are all used to the Hamiltonian, and we are all used to modeling the physics with the Hamiltonian. However, when you bring a device picture, you need both the contacts and the Hamiltonian, and also interactions within the channels. So basically, the interactions are always captured by self-energies. And it turns out that the coupling to the contacts also can be thought of in the self-energy, which is called the sigma 1 and sigma 2 in my parlance. And sigma s is a scattering in the channel, which can be several approximations, which we talk about diagrammatically. But first, and then of course, this whole formalism is based on what's called the Keldysh contour, because in non-equilibrium, the time contour is very interesting. You start from minus infinity, go all the way to plus infinity, and you wrap back to minus infinity. That's the famous Schwinger-Keldysh contour. So all Green's functions are defined in the Schwinger-Keldysh contour, and it's generally written as a time-ordered product of psi dagger correlation at two different times at two different branches of the contour. However, for all our purposes, these contours give you four Green's functions: the electron correlated, the hole correlated, the retarded, and the advanced. However, one thing very important is that all our steady state calculations depend on t minus t prime, which is the time difference, and therefore everything can be encapsulated into energy axis. And so you could write everything in terms of the energy Green's function, that is G retarded is equal to EI minus H minus sigma 1 minus sigma 2, etc. And then we can derive a current operator. I'd like to point out that in the Nambu-Spinor basis, you get these electron correlators, which are very interesting. You have the normal correlation, psi dagger, psi dagger, which is electron and hole. But you have these two extra correlators that is due to the pairing potential or superconducting anomalous pairing, which was also introduced by Gorkov and others. Okay, so when we now do device modeling with this Green's function, we have two avatars. One on the left is the so-called ballistic case, where you don't have scattering. In that case, you could write all the current operator in terms of a Landauer formula, that's the transmission times F1 minus F2. However, when you introduce in-channel scattering processes, then extra self-energy sigma s comes, due to which you cannot write the current in that generalized Landauer way. So you will have to, you can just write it in terms of a current operator that comes from the quantum mechanics of the non-equilibrium system. With this background, I'd like to last give you one small thing, that Andreev reflection is very crucial, whether you're considering normal superconductor normal systems or superconductor normal superconductor systems, specifically Andreev bound states which exist within the gap give rise to very interesting Josephson characteristics. This is just a picture of our earlier paper. And you know that Josephson characteristics, also another way to look into the Majorana zero modes. So I'll go back to the NSN system. And when we simplify our ballistic current expressions, what we get is the current can be written as a sum of three terms. One is the direct term, which is the left electron to the right electron. and then the left hole to the right hole, that's a direct term. And then you have the left electron to the left hole, which is basically the unrev process. And the left electron to the right hole is the crossed unrev process. So all these processes together give rise to these conductance features. As you can see, that the Majorana lines that I talked about can be reproduced in the conductance spectrum. And so on the left panel of the right side, you see the unrev plus direct term, which is the local and the non-local conductance. And if you separate them out into only the unrev and the direct, you can see that the lines are mainly contributed by the direct unrev process. So I'm marking figure number C here. So this kind of tells you that unrev is a dominant component of the conductance quantization. So furthermore, when we move into the spectrum, there are also higher energy aspects of the spectrum that people have never considered in the Kitaya model. You can see that it's forming these nice braid looking, nice looking braids. One thing interesting is these are what are called particle hole anticrossings. And these are higher energy, what we call nonlinear topological signatures. So this is the energy spectrum on the left panel, and we could reproduce everything with the transport too. So very interestingly, on the right, on the A panel of the right figure, you can see that this is only the unrev contribution, and you can see that the zero mode is very strongly contributed by the unrev process. But as you see, the direct process doesn't have much contribution, and unrev plus direct gives you the total terms. Now, if you can see the conductance, there's a pan out in the figure D, which you can see that there are crossings of at the zero energy, and this is typically the so-called Majorana oscillations, because if it's not long enough, you see that the Majoranas kind of hybridize. And so these are the Majorana crossings. With this background, I'll move on to the Rashba nanowire model, which is the most physical model for this practical thing. So the basic story is these are just equations. You have the kinetic energy term, the spin orbit coupling, and the Zeeman term. Okay. Now let us look at the exact picture. So now the Nambu spinner doubles. You have the upspin electron.
More than 3 minutes.
Yeah. You have the upspin electron, downspin hole, and downspin electron. And so the basic picture is in the electron space, you have the Rashba coupling that introduces upspin and downspin coupling, which moves the two spin bands. And then you have the Zeeman term, which introduces a gap. And then finally, you want to make it, and so you want to make the model spinless. So you push one of the bands above the Fermi energy so that you have an odd number of Fermi crossings. So, and then when you bring it to the Bogoliubov-Dijon basis, the space doubles, and then you open a gap due to the superconducting terms. So with this, I would like to quickly show you some transport results since we are running out of time. So these are the spectra of the Majorana nanowire, the Rashba nanowire for two different lengths and basically two different magnetic fields. I mean, you can see on the left panel that the Majorana oscillations still exist, but on the right panel, they die down only because the length is long and they don't hybridize. Now on the left panel, on this side, you can see lower left that these are the so-called local density of states from the Keldysh calculation introduced by the contacts. You can clearly see that there are the sharp zero modes that exist for the two different fields. You can also see one interesting thing that if I calculate the density of states for the total density of states for one of the fifth site or something, you can see there's a large contribution. But on the right panel, if you calculate for the middle sites, there is no contribution of the zero modes. So with this, I would like to show some conductance calculations. So you can clearly see on the lower panel that the conductance is quantized at E square by H. 2 square by H comes for a single junction. For two junctions, the conductance halves. And that conductance quantization does not die out due to the contact coupling. You make it stronger, it just broadens out, but the peak remains at 2 square by H. And then on the right panel, we show different contributions of the local and the non-local contributions. You can clearly see Andrew is a major contributor, and then the non-local contributions are completely suppressed at close to the critical field point. Now we bring in so-called dephasing interactions, the last part. This is the right panel. We bring in through the self-consistent bond approximations. I don't get into details, but with this, we can calculate what is called the phase coherence lengths, depending on how strong the dephasing is. And the general way of doing such a dephasing is basically you introduce scattering potentials and you see the correlation of the scattering potentials in space. and then we introduce it to this elaborate formalism. What you can see importantly is as you change the scattering potential, you can see that the Majorana zero modes start broadening out, as you can see on the right panel, the electronic density of states. However, you can see that the wave function mod psi square remains kind of the same, whether you've introduced dephasing or not, clearly showing peaks as well as a hybridization of the Majorana modes. Now we'll move to the conductance signatures, this is the last slide. And you can see clearly that the introduction of dephasing completely lowers the conductance from the zero mode, and which is kind of expected, and many people have predicted that impurities could cause this. But what we are showing is that impurities need not typically cause the zero mode to fail, but this is because of fluctuating scatterers that we could actually result in a reduction in the conductance. Whereas I should remind you that contact coupling does not do this. As you increase the broadening, it will still remain quantized at 1, I mean E square by H, but it will only broaden out. So that's the kind of difference between dephasing and the normal contact broadening. I'd like to point out last year we showed some very interesting effects about dephasing in normal superconductor normal junctions on the Josephson characteristics and modeled a few experiments. And we could see that dephasing kind of suppresses all the local channel perturbations and things like that to give you something closer to the experimental result. It gives you something that transits you from the coherent ballistic regime all the way toward the diffusive regime. So with this, I go into the conclusions. What we showed is the nature of the Andre reflection process and the zero bias peak, local and non-local conductance contributions, and the role of dephasing via self-consistent Born approximation, and dephasing versus contact broadening, as you can see clearly here. And these are a few works, and a few more are going to be submitted, and so you could have a look at them. And last but not the least, I'd like to thank you for inviting me here. And these are my collaborators. And some of the works were done by undergrads in IIT Bombay, as is listed here. And that's Praveen who started the work. He's in Stanford. Atri and Chaitrali are currently doing this work as BTech students and dual degree students. So thank you very much again, and we can take questions.
Thank you very much, Bhaskaran. So we have time for 1 or 2 questions. Just raise your hand and go ahead and ask a question. Okay, so I don't see any raised hands. So can I ask, can I abuse my position as the chair and ask a question?
Yeah, sure.
So in the Keldysh, yeah, this part, this simulations that you were showing, I didn't see details of the simulations. I saw that you have a lattice of what, 100 sites in the LDOS plots that you're looking at?
Yeah.
So what are the rest of the parameters here in the,
Sure.
Yeah.
So we've written them all in the paper here. We didn't show too much. Okay, so first of all, the number of sites and the length of the system we have taken is about 1600 nanometer. So it's 100 sites only because, you know, that lattice spacing and the hopping parameter are related. And
no, I can't see very well. Could you go back to the full screen mode just for, yeah. Yes.
Yeah. So the number of sites is not like related to the length. Length, it's related to the length in a very arcane way. So it's about a 1600 nanometer length. So the coupling, so the hopping parameter is adjusted based on the lattice spacing, which we have fixed at some number. Next step is that based on that, the superconducting order parameter is fixed at based on the values that we know about the system, that is, aluminum coupled to the. We have taken it from literature. It's about a few 0.25 millivolts or something, 0.02, yeah, something like that. And then we have taken the hopping to be 100 times larger than that. And the contact broadenings, what we have taken, is typically of the order, if you can see here in the lower panel, the gamma is a contact broadening. We have taken it at the order of the pairing potential or lower than that.
So just one final minor thing. Why do you say that the what you've shown in the LDOS plots is not really related to the length? Because the modes
it is related to the length. It is
supposed to be the, and it is, right?
It is. What I said is there is a very funny relationship between the length and the number of sites. That's all. Because it's based on the hopping parameter which we get from literature. So T is equal to h square by 2ma square discretization. And so I don't have a mapping. That's all I mean.
Okay. Yeah. Okay.
Sorry about the cursor issue. I should have fixed it in PowerPoint. Yes.
No, the talk was so fluid that, I mean, later on the cursor was not visible, but nobody complained. So it must have been fine.
Okay.
So any further questions?
Can I ask a question?
Yes.
Go ahead.
Yeah, Aditya. So, so just wanted to ask you, so you showed this, so did you discuss anything about the differentiation between these Majorana zero modes and read bound states?
Very good question. I did not discuss deliberately because so there are these in the literature. They talk. I only talked about the properties of the zero mode if you found it correctly. Okay, good. Now let us say we are talking about these quasi-Majoranas, which is of great interest these days. So there, what happens is we'll have to introduce. That's why I showed this structure. It's a split gate structure, and the gate potential will introduce a so-called potential profile in the normal region.
Right.
And that will give rise to some zero modes that are close enough to the Majorana mode, but these are actually regular Andreev modes. That we have not simulated yet, only because we wanted to show the role of dephasing on the pristine zero mode. Now this, yeah, so we are still, this is still a work in progress. We haven't yet started that, but I'm quite familiar with what you are asking, and we have not talked about it.
Okay.
Okay, so thank you very much, Bhaskaran.
Thank you.
If you could kindly unshare your screen, we can move on to Arijit's talk.
Yeah, sure. Thank you.
Thank you. So Arijit, go ahead and share your screen. Okay, so the next talk is by Arijit Kundu, also from IIT Kanpur, and he'll talk about signatures of Fermi-Arc correlations in collective modes in thin film biosignators. Go ahead, Arijit. You can start. I'll let you know in about 15, 16 minutes. Yeah.
Please unmute. He is not unmuted. Ask him to unmute. You can unmute him. Ask him.
Oh, so
Yeah, we can hear you. So you can start.
okay. Yeah. Was I unmute? Okay. Yeah, so I'd like to extend my appreciation for conducting such a nice meeting. This is, I think, third or fourth time. And especially in this time when you cannot really travel, this really helps us to some extent to kind of know various colleagues what they are working on. So in this talk, so I'll briefly introduce wild semi-metals and their surface states, which we call Fermi-Arc states. So I'll talk about some simple models and boundary conditions to kind of visualize these. And basically focusing on understanding of some non-local effects, spin-spin coupling and collective modes in the system. So this talk is based on these three papers. The last one is in archive and is done by basically these two PhD students, and he was a BTech student. He's now been Wiseman with a former student of Sumati Rao, Dibbo, who is at Paris, and Harfarti from IU Bloomington. So I will not be talking about some other topics that we are working on in this group, are essentially things like quantum transport in topological systems, time periodic quantum systems, recently Moire lattice systems, Lagrangian liquid and RG studies in topological edge modes, as well as a correlated spin system in frustrated lattices. So with that, let me start by introducing wild semi-metal that I'm sure all of you are familiar with, or most of you are familiar with. There may be one or two students, a few students who are not familiar yet. Essentially, this is a wild semi-metal you can think of is having a Dirac node, and then you break certain symmetries, either time reversal symmetry or inversion symmetry, which separates this Dirac node into momentum space. So it's a Dirac node, which is 4x4 Hamiltonian essentially. Then you break symmetry, break into 2x2 Hamiltonians, which would be individually wild nodes. So when I say you separate them out, it means that they kind of know from where they're coming from. So they can always appear in pairs. So the wild nodes in any system always appears in pairs. So typically they appear because of accidental accidental degeneracies, but they must appear in pairs. So what it means that in the bulk of the Hamiltonian, if your chemical potential is somewhere near the charge neutrality point, the low energy Hamiltonian will consist of some 2n number of these wild nodes. It can also have other Fermi surfaces, but forgetting about other Fermi surfaces. So the bulk Hamiltonian will consist of some 2n number of these wild nodes which are otherwise not related to each other. So the bulk of the Hamiltonian is only block diagonal into these 2n blocks. But because we know that these wild nodes are coming from Dirac nodes, somehow the surface retains some of this information. So when you have a surface, when you have a finite geometry, then on the surface Brillouin, the Fermi surface tracks the parent Dirac node, if you wish, from the wild nodes. So this statement is a little confusing and is strictly speaking not true. So how these Fermi surface will join the wild nodes depends on your surface termination. Depending on surface termination, these various Fermi surfaces, which look like arc, will join various pairs of wild nodes. So they will always join pairs of wild nodes with one property, which is that these wild nodes must have opposite so-called chirality. But in simple manner, what you can think of is that so the surface Brillouin will have a set of arc-like Fermi surfaces. So these arcs must join pairs of wild nodes. So these are what we call Fermi arc states. So these are surface states in a way that they have a finite localization length, but they are a little bit strange in a way that this localization length diverges as this arc comes close to the wild nodes. Now, for every arc, there is another arc on the other surface, and these two arcs are connected by the bulk wild nodes. So this is how the surfaces are kind of interlinked to each other and give rise to non-local effects. More importantly, if the top surface, this top surface Fermi arc disperses in one direction, then the bottom surface Fermi arc disperses in other direction. So these are essentially the properties of wild system. They are made of wild nodes. The surfaces will have Fermi arcs, and the Fermi arcs are chiral in a sense that they can disperse along one direction. And whichever direction they disperse, if you look at the bottom surface, it will disperse in the other direction. So the top surface and the bottom surface together, these two Fermi arcs close a complete Fermi surface that gives a complete closed loop of Fermi surface. We'll see some of these a little bit more clearly later on. Okay, now as I said, that even though your bulk of the Hamiltonian doesn't know how to pair these various wild nodes, the surface somehow knows how to pair them. So when you deal with a system with finite geometry, it's useful to write these 2n number of wild nodes into pairs of them in a way that we know that the surface will kind of join these two. And this can be extended to any 2n number of wild nodes. This simple idea. Now, what I will be talking about is called thin film geometry. So a thin film has various implications here. One of them is various non-local effects. Those appear in this thin film geometry. So the idea of thin film is slightly convoluted in wild systems, which is because typically if you have a topological insulator, for example, which has a bulk cap, then you know that the surface states will be localized and the localization length will depend on the bulk cap. Now, as I said, the surface states in wild systems are localized, but the location length of the localization diverges near the wild nodes. So it's not enough to characterize the thin film limit by just mentioning localization length. But on the other hand, the number of such surface states is fixed. They just are the number of momentum points between the two wild nodes. So in a way that once we increase the thickness of the sample, after some thickness, the properties of the sample must become independent of the thickness. Okay. So that when this change is taking place between a very thin sample to a sample thickness where the change is becoming fixed. The change is kind of is not there anymore. So in between there is the thin film limit. Okay. So and in hindsight, we know that there is only one length scale in the whole problem, which is the separation of the wild nodes in the momentum space. So whatever thin film we'll be talking about must have a length scale which is coming from the separation of the wild nodes. So this is how the thin film limit is fundamentally different here than, for example, a topological insulator, where the separation momentum space doesn't play any role. Okay, so this is just one slide of how one can think of these surface modes as topological edge modes. So, for example, we know that for a Dirac equation, a 2 cross 2 Dirac equation, 2 cross 2, simple Dirac equation will have a Chern number which is given by the sign of the mass. Now, if the mass itself is a function of one of the momentum, then as a function of momentum, the Chern number of the other two direction, so it's essentially a projection of the system in the other two direction, that Chern number can change as a function of the third momentum. And how that change takes place can give rise to edge modes that can disperse in different directions. So this is the easiest way of thinking about Fermi arc states. These are nothing but quantum Hall edge modes where the mass of the system is a function of one of the momentum. So with that, one can solve some boundary condition problems semi-analytically. So now this is an interesting slide. So this shows you how the low energy band structure of any generic while system would look like near the two while nodes. That it has these bands. So the details of the bands can differ from system to system, but essential features are that it has these low-lying bands. These low-lying bands are the ones which contains all the Fermi arc states. All the surface states are there. Now these bands are bound by these two momentum, ky minus k0 and ky k0. These were originally the position of the wild nodes. So all the states which are Fermi arc states lies in between these two momentum, and on the side of the band, these are bulk states. And there, of course, there are 1/L separated other bulk bands and so on. The most crucial feature of this thing is that you put a chemical potential, you put a Fermi energy somewhere between this band and the first bulk band. You can also put anywhere else, but it's just easy to visualize here. You put a chemical potential here, the Fermi surface is now this elliptical, I mean, it looks like ellipse is not really ellipse, of some kind of closed loop. The important feature is that a part of the Fermi surface are supported by the bulk states, which are these solid lines here, whereas a part of the other parts of the Fermi surface are supported by Fermi arc state from two different surfaces. So this is the crux of the interesting problem here, is that individual Fermi surfaces contains bulk states, contains surface states of one surface, and contains surface states of the other surface. And these three together makes the Fermi surface close. So any property which relies on the closeness of the Fermi surface will inherently become non-local in this system, because the Fermi surface gets closed by having support from bulk as well as two different surfaces. And as I said, I mean, these dotted part of the Fermi surface, so these the electrons here can disperse only in one direction. This two dotted part, these surface states, they can disperse in other direction, and they leave on two different surfaces. Okay, so with that, let me talk very, very briefly on RKKY interaction in the problem, but I will focus mostly on the collective modes. So as we all know, the RKKY interaction is essentially, it captures the spin susceptibility of the problem. So when you have two spin put on an electronic system, the effective coupling between the two spins are carried by the underlying electronic degrees of freedom. One can think of essentially an information from one spin is going to the other spin through electron, and it's coming back through a reverse path. There's a very simple notation of that. One important result of the RKKY, which is going to be interesting, is that So if we have a purely spin polarized, a purely chiral state, that means electrons can move only in one direction, then of course there is no way these electrons can bring back the information, so all the RKKY coefficients will going to be 0. If the state is such that this particular spin can move in only one direction, another spin can move in the other direction, in that case the up spin electrons cannot bring back the information. So the RKKY interaction of the Z component, for example, is going to be 0. Now another property which is going to be useful for us is that for the Fermi arc states, is not only they are chiral, they are also spin polarized in some basis. Whichever basis the original while nodes were written, the Fermi arc states is going to be they are going to be spin polarized, and they are spin polarized in opposite direction for opposite surfaces. Okay, so there are some other details. Now, what you can say very briefly is the following two statements. So if we put two spins here on the same surface, then even though the surface is spin polarized in x direction, the RKKY interaction along the x goes that rapidly goes to 0 as we increase the thickness, because along that spin direction, because of the mechanism we discussed here, for a chiral state, for a chiral state, the spin component z is going to be 0. For that spin component, so this becomes a anisotropic spin-spin correlation if you put the two spins on the same surface. Now, what is interesting is that if you put two spins on opposite surfaces, now these correlations are done mediated by the bulk states. So we see that this correlation also decays very fast. They have certain symmetry properties which we are not going to talk about here. What is important here is that in either cases, so there is a optimal thickness at which one can obtain a maximum spin-spin correlation, and then it decays. So this optimal thickness is a competition between two facts. One is that as we increase thickness, the surface states are more they are more better formed. The Fermi arc states are better formed, and because they're better formed, the surface has more density of states. So this density of states can couple to the spin more strongly. But with increasing thickness essentially, if the two spins are two different surfaces with increasing thickness, the bulk cannot really carry the information back and forth easily. So that leads to a decrease in the overall spin-spin interaction. So yeah, so this is an example where such non-local properties can give rise to a thin film limit for an optimal thickness where you have the maximum non-local effect. Okay, let me move on to the collective modes. So essentially, we are talking about plasmons. So if we have a thin film geometry, and again the same statement is that we have two Fermi arcs on top surface and bottom surface, and we're talking about, okay, are there charge modes, collective charge modes supported by them? So this falls into, okay, so this is a brief idea of what we expect. So there could be particle hole processes involving both surfaces. So electron from one surface.
We have about 4 minutes.
Okay, yeah. So there could be particle hole process involving both surfaces, which is suppressed because the Fermi arc states are spin polarized and they are orthogonal to each other on the two surfaces. So this particle process involving two surfaces will be suppressed. What is the predominant effect here would be the screening of the one Fermi arc states because of the presence of the other dynamically. And especially at small q, the interaction is long range, and then the two surfaces can visibly see each other. Okay, so this is how we typically, so this is a heuristic way of thinking of it, that we have two surfaces, and one can write down some dielectric function for involving two surfaces. So the general statement of any of the systems is that, so we get two plasmon modes. One is a short range acoustic plasmon mode, and one is a optical plasmon mode, is a long range. So the acoustic, what is more important is that the omega proportional to q mode is an out of phase oscillation, whereas
Yeah, come in.
whereas the omega proportional root Q mode is an in-phase oscillation of the layers, and that plays an important role. We'll talk about it. Okay, so let me summarize this slide in 1 minute. Is that so for any such two-layer system, the general statement is that we get two plasmon modes. One is omega proportional to Q, and one is omega proportional root over of Q. The omega proportional to Q is an out-of-phase oscillation. That means the charge on the two surfaces are out of phase. That means one has a positive charge, one has a negative charge. Whereas the omega proportional root Q, which is optical plasmon, has an in-phase oscillation of charge. So let me skip some of these and go into here. Essentially, one can show that, interestingly, and this is the only unique system we know of, is this wild system in presence of Fermi arc, is because the chiral nature of the Fermi arcs, this individual non-interacting susceptibility behaves differently than a normal 2D system, which essentially leads to the fact that the optical plasmon mode is an antisymmetric mode. So instead of a symmetric optical plasmon, wild system can host an antisymmetric plasmon mode. So this is a heuristic statement. So we verify this numerically. We solve a density correlation problem in this 3 dimension. We make a matrix of in the basis of ZZ prime. Not going to go into detail. So essentially, these are the results we get. So this is the left hand side is a plasmon. This green line denotes the sharp plasmon modes in otherwise particle hole continuum, and this is a gap in the particle continuum. The right hand side is the two plasmon modes for other system, for example, Dirac system. So this root Q mode, this wild system, this plasmon is not only this is unique in a way that this is also supported by both surfaces. This is a support of the plasmon modes on the both surfaces, and one can look at the eigenvectors of these modes to find out that they indeed are purely antisymmetric oscillation of charge. So this is a comparison to Dirac system. So root Q mode Dirac system is a symmetric oscillation of charge. A Q mode in Dirac system is antisymmetric oscillation of charge. A root Q mode in wild system is an antisymmetric oscillation of charge. And very important implication of this is that this system becomes immediately a natural waveguide. It can confine electric fields if we want to use them for the application of optical transmission. The electric field of appropriate frequency can be purely absorbed.
Perhaps you can wrap up in a minute or two.
Yes, I'm basically done. So this is my conclusion. So what we talked about is that Fermi states are essentially topological states with interesting spin momentum locking. They are always connected to each other through the bulk, which always naturally to give rise to non-local effects. And of course, it opens possibility of using them in control of correlations and collective modes. Okay, thanks. Yeah, please.
Okay, Arijit, thank you for the interesting talk, and we have time for some questions.
I think Amit and Shantanu wanted to ask some questions.
Sorry?
I think Amit and Shantanu, they wrote in chat.
Yeah. So Amit, go ahead and ask your question.
Yeah. So Arijit, I have a simple question. So
Yes.
this naively, I would think that this Fermi arcs are one-dimensional.
Well, I mean, they are two-dimensional. Their wave function lives in 2 dimensions. The dispersion is predominantly 1 dimension.
I see. Okay. So because of that, you get this root Q.
Yes.
Okay. And Q is what direction related to the, let's say?
It doesn't matter, any direction. So the proportional factor to the root Q will depend on the direction.
I see. Okay. Okay, fine.
Okay. Shantanu Mukherjee, you can go ahead.
Yeah. Hi, Arijit. I had a hi. I had a quick question. So typically, we start off by looking at these models within a single orbital picture. So if I were to think about, let's say, a multi-orbital picture and the Coulomb term had other contributions than in the VQ that you consider, would you introduce them as a matrix equation? How can
Yes. Yeah. So so one can think of these having. So essentially, you have to solve a set of coupled equations like this. If you want to look for some sort of susceptibilities, then okay. I mean, this is my understanding. Is again, Shantanu, I may be understanding wrong what you're asking, but essentially, if you have multiple orbitals or multiple Fermi surfaces, multiple ways electrons can scatter among themselves, this becomes more and more involved in a way that they can be coupled.
And we cannot consider them more classically, right? It has to be a more quantum treatment of the VQ itself.
Right. So okay. So you can consider classically, but if you so there are works where you can consider okay, but in classically you have to be careful because let me say it this way. So for example, you want to discuss the plasmons of Fermi arcs in a semi-classical manner. You can write down like wave equations and stuff like this. But you have to also think of how these electrons can come from, let's say, the bulk of the system. So you have to add in some source term,
right,
or some current term. Yeah, that gives a qualitatively correct result, but I'm not sure about how.
Okay, that's okay. That's okay. We can talk about it later. Thank you.
Yes, absolutely.
Yeah.
I think Sumiran wants to ask a question.
Okay, Sumiran, go ahead.
Hi, Arnab. Just a short question. This thin film limit that you have considered, that is still larger compared to the microscopic lattice, or not? It can be comparable, or doesn't matter?
Yeah, so it depends. I think it will be larger because you see, typically this length scale is simply 1 by the separation of the momentum scale, essentially. And the separational momentum scales are of the order of 0.1 angstroms, of the order of that in some of these materials.
Okay.
So it will be like few tens of angstroms. So it will be like yeah.
I see. 10 layers or something.
Yeah, something like that.
Okay, thank you.
Okay. I don't see any other raised hand at the moment. So thank you, Arijit.
Thanks for
talk. Yeah. And let's move on to the next speaker. If you could unshare your screen.
Yes.
Yes. Gaur, could you go to the full screen mode?
Yeah. So now I'm in full screen mode.
Yeah.
Am I audible?
Yes, you're audible. Everything is fine. So just go ahead. Your talk is a 12-minute talk. I'll tell you when you're done speaking for 10 minutes. Okay.
Okay.
So Gaur Jana is from NICER. He's a PhD student here, and he'll tell us about half metallicity at finite temperature in the model insulator. Go ahead, Gaur.
Okay, so I'll start by thanking the organizers for giving me opportunity to present my work here. So today I'll be talking about the half metallicity at finite temperature in a MOT insulator. So this work has been done with the collaboration with my supervisor Anamitra Mukherjee and Abhishek Joshi and Subhajit Pal. So this is the brief outline of my talk. So first I'll talk about the model and then method, and then I'll go to the result part, and then I'll summarize. Okay, so we study the Arnick-Hubbard model. So the model Hamiltonian is given here. So where the first two terms corresponding to the kinetic energy term for the first, the first term corresponds to the nearest neighbor hopping term, and the second term is correspond to the second nearest neighbor hopping term. So and there is staggered magnetic potential plus delta in the A sublattice and minus delta in the B sublattice. Okay, so there is an Hubbard interaction U, and we have mu is the chemical potential here. So we put a small magnetic field H. So why we put that I'll talk in the I'll tell you in the next slide. So the Hubbard model is important because of its diversity of capturing band insulator, MOT insulator, and non-trivial metallic phase like a half metallic phase. So there some previous work where these phases can they have shown. So some of the references I'm giving here. So the method we have solved by using so-called mean field Monte Carlo technique, The technique is based on the Hubbard-Steinhaus decomposition of the square of the operator, number operator and the spin operator, which comes from the two-body interaction term. And this introduced actually the auxiliary phi coupled to the density and the mi coupled to the spin. So which actually allow us to write the partition function, which is given here, and then we'll finally extract the effective Hamiltonian from this partition function by keeping the spatial fluctuation only and using the saddle point value of the phi. So this Hamiltonian has the rotational Newtonian form, and we are in T2D. So to break the rotation symmetry, we put a small magnetic field to avoid the Marmin-Wagner issue. So so I'll start by the limiting, I mean, from the of the limiting cases of the model I just talked about. So in this cartoon picture on the right corner, so there are two sublattices A and B. A has plus delta potential and B has minus delta potential. So at half filling, when U is 0, so this delta opens up a gap and gives us band insulator. But when this delta is 0 and U is large, this prefers singly occupied sites and give us more insulating phase. But when both U and delta present, so the gap actually reduces and is represented by this blue curve. And if we increase the U, so the gap will reduce and eventually it will go to 0 when U equals to 2 delta. So in the left panel, so the spin polarized resistivity for in the regime when U equals to 2 delta shows that so the both channel has negative slope, and it is monotonic in with temperature. So that means it's actually band insulator. So I should have mentioned that the spin polarized resistivity has been calculated from the Kubo formula. Okay, so for the case when U much greater than 2 delta, the resistivity curve shows that the both channel in the low temperature regime has negative slope, and it's non-monotonic with temperature. So that means it's actually in the mod insulator. So throughout the calculation, we fixed the delta is as 1 and T prime as minus 0.2. So now when U comparable to 2 delta, the low temperature density of states shown in the left panel, that the up channel has finite weight at the chemical potential, so it's metallic, and the down channel is gap, so it's insulating. So this can be seen in the spin polarized resistivity also. So where the up channel represented by the blue curve has positive slope, so it's so this channel is metallic, where the other channel has the negative slope, so it's insulating. So so in this so here only one conducting channel is there. So again we have calculated the polarization from the current using this formula. So the polarization is plotted in the by the so represented by the red curve, where at low temperature the polarization is 1, and again it's as you increase the temperature it's actually decreasing. So that means at 0 temperature, the half metallic phase has the 100% spin polarization, and it has a finite pi magnetic correlation as represented by the blue curve. So when we are in the mod phase, means U greater than 2 delta but close to the 0 temperature half metallic phase, the low temperature density of states shows on the left panel that the up channel has smaller gaps and down channel has the larger gap. So it's so it has an asymmetric gap in the density of states. So which can be which actually has been found in the previous study using DMFT by Arthis group. So now if we increase the temperature, so then the right corner, I mean the panel in the right corner shows that the one channel which has smaller gap gains weight faster than the other one, and this reflects also in the spin polarized resistivity in the middle panel flat. At low temperature, the both channel has negative slope and both are insulating. But as we increase the temperature, there is a change in the slope of the resistivity for up channel and gives us metallic phase. So here also one conducting channel is there, the other is insulating. Again, the spin polarization plotted in the right panel represented by the red curve has the behavior that at low temperature, when the system was in the mode phase, means gap phase, the polarization was 0. And when the change of the slope in the resistivity happens, then the polarization picks up the value 1, and then it's actually going to 0. So that means at finite temperature, the half metallic phase we are getting at 100% spin polarization, and also it has pi-pi magnetic correlation. So why this is happening? So if we look at the density of states at the chemical potential plotted against temperature, so the both channel up and down, both are actually gaining weight, but the up channel is gaining weight faster than the other one. So why? If we look at the distribution of the moment at low temperature, the moment distribution sharply peaked, and as we increase the temperature, so the distribution of moment gets broadened, and this gives actually the inhomogeneous distribution of the moments. From there, the both kind of electrons up and down get scattered and gain weight, but as the up channel has smaller gap, so it gain weight faster than the other one and hit the metallic window. So it's which gives the half metallic phase at the finite temperature. So to conclude, so here is my summary. So due to the competition between U and V, we get a zero temperature half metallic phase with 100% spin polarization strictly at zero temperature, and which has an antiferromagnetic correlation. And due to the presence of asymmetric gap in the spin channel, the scattering of electron from the diffused moment fills up the gap in one spin channel and leads to the half metallicity at finite temperature with 100% spin polarization. So we have looked at till now a single delta value, but this can be tuned over the U and delta phase space, where which is shown in the right corner. So over the regime of delta and U, we get a finite temperature half metallic phase. So this model can be realized in a coalitemic systems. Yeah, thank you.
Okay, thank you, Gaur. You finished 2 minutes early, so we have time for questions. Okay, so I don't see any questions, and Gaur is anyway a student here, so I can ask him all the questions I want by just dropping into his office. So thank you, Gaur, for the talk. This concludes this session. I'll hand this over now to Anamitra, and yeah, go ahead. Thank you.
Thank you.
Thank you to all the speakers.
So thank you, Ravi, for chairing the session, and thanks all the speakers for nice talks. We are, I think we can start at 11, Ravi. That is okay.
Yeah, it's 10. Yeah,
so we can keep the usual time at 11. And so what we'll do, just as an announcement, after the last talk, we will have the discussion on the meeting here itself, so that we can wrap it up before lunch. So we request everybody to stay after the last talk by Paramita Datta, so that we can have a final discussion on the meeting. Okay, so we'll meet at 11.
I think Ganesh is already there.
So the next session chair and the speakers, I request them to be around so that I can check their screen, etc. Okay.
So I think I'll have to sort of remove the co-host this thing from the current set, right?
Yeah. Sure. I can do that. Okay.
You should mute.
Right. Hi, Ganesh. You can
Hi.
hear me?
Yes, I can hear you.
Okay, so good. So let me see if the
Good.
speakers
So I
are
see
around.
Manas Kulkarni is online. Manas is online. Utpal Roy.
Yeah, Utpal Roy is also online.
And there's Jayant Bera, Devotamandal. Yes, they are all online.
Okay, so and 3 contributed talks. Let me just see.
Joyanto Bera is online.
Yes.
Hi, Ganesh. Hi, everybody.
Oh, Manas.
Hello.
Hello, Manas.
Yeah, hi. Yeah, so maybe I'll just shortly try sharing my screen if you give me a few minutes, 2 minutes.
So why don't you want to? Are you ready to do that now?
Just give me a minute.
Sure. Yes. Maybe we can ask Utpal Roy.
Yeah. Utpal can go ahead. Yeah.
Yeah, go ahead. So Ganesh, the last 2 speakers, and I don't see them here.
Am I audible?
Yes.
Yes.
Last 2 speakers, right?
Yeah.
Okay, we'll see when they come up.
Okay, go ahead. Share your screen.
So
Ganesh?
Utpal, hi. So Ganesh.
Yeah, hi. Am I audible?
Yes.
Yes.
Okay, I'll try to share my screen.
Yes.
Yeah. Do you see my screen now?
Yes.
Yes.
To try full screen. You'd like to have a slideshow mode?
Changing slides are changing.
Slides?
No, it
there's
did
some
not
lag.
change.
Yes. Could you go to slideshow mode, or would you?
Yeah, go to full screen mode maybe. Or presentation. This is PowerPoint, right? Maybe the screen is stuck or something. Yeah, I can see it in full screen.
I only see the title screen. I didn't see the screen.
Now it has again gone. So maybe you can try it once more. Hi, screen is visible. Maybe try to go to full screen.
So I only see this one slide, is Bose-Einstein condensate.
Yeah.
You too, right, Anamitra? You don't see.
Yes, I can see only one. The one with the Einstein, Bose, and other Nobel laureates.
So yes, very aspirational slide. Yes, always. Could you try moving down to other slides? Paul? Co-host.
Yeah, I can see it in full screen now.
Yes, the title screen, I can see it. I can also see your cursor. Could you try
Just,
going down?
Yeah.
But we can't hear you anymore. Have you muted yourself?
How, Utpal, you're muted.
Utpal, you're in mute, so we can't hear you.
Yeah. It was muted.
Oh, yes.
So full screen is visible, and I'm changing the slide. That is also should be fine now.
No, we cannot see. Oh, yes. Now we can.
Yeah,
see.
now
Could you
it's
go further down, just to make sure. Go past the Nobel laureates. Could you change the slide again? What I see is I only see the Nobel laureates. That only that second slide.
Is the motivation? Do you see that?
No, I don't see the motivation.
Not really.
So either there is some lag.
Maybe try to change the slide without being in full screen. Just go out of full screen and try to see if you can scroll up and down.
This is a strange problem. Right? So far.
There might be a network issue, it seems.
Yes, quite possible, yes. Or perhaps if you have a PDF version of the talk, I don't know if that is suitable. Then
yeah,
it's something to do with PowerPoint.
Yeah, so maybe I think he has logged out and is trying to log in again.
So
I don't see him here.
Manas, until then, Manas, would you like to share your screen?
Sure. Shall I try it?
Yes, please.
Nice.
See your screen?
Yeah. So should I make it full screen?
Yes.
Yes, please.
Yeah.
Okay, we see a pointer. Very good.
Do you see the pointer also?
Yes.
I see the pointer.
And do you see me moving
the slide?
Okay. So you see me moving the cursor also, right?
Yes, man. You're all set. Yes, everything is fine.
Okay.
Cursor works.
You see my cursor, right? You see my cursor?
Yes. I see your cursor. Yes.
Okay. So I will stop sharing. Yeah?
Yes. Thanks.
Okay. Thank you.
So,
Jayant,
yeah.
Could you share your screen?
Hello, sir.
Hi.
Hello.
Hi.
Am I audible?
Yes.
Yes.
Yeah. So I'm sharing just.
Yeah, I'm sorry that it was disconnected again.
Oh, yes. I think there's
That's
some
okay.
problem.
Yeah, I'll now connect to other source of it, and now just see whether it is changing now. Is the first slide?
I see the titles.
Yes.
Yeah, now I'm changing without making a full screen.
It is changing.
You see the Nobel.
It's changing. Now I'll just check full screen.
Second froze. There may be network issue.
Hi, can you hear us, Utpal?
I think screen is frozen. I mean, like the mouse is kind of stuck.
After this, yes. So must be bad internet.
Yeah.
Utpal, can you hear us? Utpal?
No, I think he has logged out again. Just
This is not very good news.
yeah. So in the meanwhile, should we check the other guys as well? I think Jayant Bera and Devottam Mandal are here.
So shall I share my screen?
Go ahead and share.
Please do.
Okay. Yeah, I have done. Is it visible?
Yeah, it's visible. Go to full screen and go up and down.
Yes.
Yes, it's full screen. Yes, I can see your cursor. Yeah.
It's moving.
Yes.
Cursor is moving.
My cursor also. Is it fine?
Yes, it's all. You're all set.
No,
thank you.
So I'm stopping. Yes. Sir.
Devottam Mandal.
Share your screen.
Yes, I'm sharing.
One, two, three, four, five.
So is it visible now?
It's visible full screen. We can see your marker.
Will you change slides? Yes, very good. You're all set.
Okay.
Good.
Thank you.
Thank you. Please
I will
unshare.
stop sharing then.
So the first speaker is still, and the last speaker, I still don't see her.
Yeah, the Paramita Datta is not yet here, but she is in a different country. I think it's early morning for her. Probably she'll join in the middle, I hope.
Yes.
So Utpal, yeah, he's back. Let me make him a. Okay, I can see his screen.
Yes.
Yeah.
Hi.
So just check. Yeah, this is the third network connection. Okay. I'm sorry for the delay. Is it full screen now?
Yes.
See full screen. You see your title slide.
Okay, I'm now changing. Is it changing?
Yes. Now you see the second slide. Nobel laureates. Could you go to the third slide? Okay, good. Very good.
Third
So
slide.
I think the third slide for the first time.
So I can
Could
start. I can start.
I don't see your pointer. Oh yes,
So
now I see.
Do you see my cursor?
Yes.
Yeah.
Now we see.
So good.
Yes. Very good. Thank you. Thank you. Thank you. So I suppose we'll start.
Okay, so I'll turn over to you, Ganesh, and thank you for chairing this session.
Thank you. Thank you. Okay, so welcome back, everybody. So welcome to the last session, hopefully the most interesting session. So we have a list of speakers. We'll start with Utpal Roy from IIT Patna. So you have 25 minutes. I will let you know after 19 minutes. Please start. Over to you. Utpal? Anumitra, you hear Utpal speaking?
No, I don't. I think I don't hear him.
He is unmuted, but we can't. Now we can't hear your voice.
Yeah, he's unmuted. Utpal, if you can hear us, maybe go out of the full screen and just try to see if.
Okay, let's see.
Is he back? No, I don't see him as yet.
Back yet. So sorry for the delay. We'll try to.
Yeah, so sorry for the delay, guys. Yeah, I don't have his number. Any of you have Utpal's number? Utpal.
Hello, it's me, Janta. Hello.
Hi.
Hello.
Hi, Jayant.
Yeah, actually Utpal is my supervisor. I can give you my number. You need Utpal's number? Yes.
Hello, who is speaking?
7481.
Just,
I am Janta. He is my
okay.
supervisor.
Okay, please give me the number.
7481.
Okay.
99.
99.
7862.
7862.
Yes.
Okay, thank you. Thank you. Let me try to call you.
Okay.
Anybody has a phone? I left my phone in the car. Number to line. No, he's not picking up. Let's try. Ganesh, maybe should we proceed with the next talk?
Yes, let's do that.
Oh, the Utpal is here. Utpal is just here. I see him now. I'll make him a
Yeah,
co-host.
let me give a last try. Yeah.
Okay.
Yeah, just I copied the slide. Another nation. Yeah, do you see my screen now?
Yes.
We hear your voice too. So go ahead, please start.
Okay. So now I've made the full screen. I hope this should be visible.
Yes.
Okay, so thank you very much. So first of all, I would like to thank the organizers, Professor Mukherjee, Professor Chandra, Professor Nandi, and Professor Shah for organizing this very successful online event and inviting me to talk about my work here. In fact, I have been in this meeting for last couple of years. So yeah, coming back to my topic is ultra-cold atoms in disordered optical superlattices. So as I have seen that, not many talks are there in ultra-cold atoms. So I thought that I'll devote one slide for the students. So the history started from 1925, where our scientist Asian Bose has discovered the Bose statistics for photons. And then along with Einstein, they discovered Bose-Einstein condensation. Then it took 70 years to achieve it in experiments in 1995 by Ketterle, Wyman, and Cornell for sodium and rubidium atoms. And they attracted Nobel Prize in Physics in 2001. And since then, this area has become quite emerging, and this system has become a very important candidate for achieving quantum technological applications. So, and this system is very important and very special because it is a highly tunable object and highly coherent as well. So that is why, a lot of people are applying it for technological things, achieving the quantum logic gates and a lot of quantum information applications. So here are some list of some applications. These are like one can achieve BEC, but then how does it look like? So then, there are solitone vortices, Faraday waves, and there are phase transitions. And then different applications, mainly, I'll point out here this Anderson localizations, negative temperature. This is the is a appropriate examples for quantum simulations through the variations of the external trap parameters. So BEC is kept inside a potential trap, and then the dynamics is actually observed. And for different potential traps, by engineering the traps, one can achieve different technological aspects. So recently, the observation in space in 2020 and before, it started in 2018 in space station. So I'll mention about the dynamical equation here. You can see that there's some Gross-Pitowski equation in the bottom, and which is the actual dynamical equation of this system, Bose-Einstein condensate in 3 dimensions. Now the first term, which is the blue circle, is the nonlinear term, which makes it, non-trivial at the same time very interesting system, and it is experimentally tunable through phase-back resonance. And the second thing, which is red circle over there, this is the external confinement. which is the thing which I am going to explain here, that how optical lattice can tune the system. But this has to be kind of with time, it has proven to be a better candidate for tunability compared to the nonlinearity. So most of the things, applications are coming by tuning the external trap, which is here. Now, these are some of the works which I'll not get time to mention, but these are the works which is related to BEC in external traps, external potentials, various potentials. The first one is in the end of 2019. This was the weak measurements, the weak value amplifications in BEC for the first time. The second was the analytical method, the model we provided for double well, tunable double well, how the dynamics behave inside a tunable double well. And the third one is the first time we are proposing for fractional revivers, quantum fractional revivers in BEC, which is going to appear in few days. Now, here I will emphasize on optical lattices, and I'll start with bichromatic lattice, and which is a kind of the starting point and a most important candidate for quantum simulation. And this is the candidate which is more or less handled in Bohr-Sabot models. But here, handling analytically the dynamical equation becomes really non-trivial. So here I'll say that what is bichromatic lattice. If you look at the top plot here, so this is a single periodic lattice, which is optical lattice, we say. And if the period is kind of half of the period, the second one is the half of the period, but this is also optical lattice. But if you superpose both of them, superpose both the standing waves in experiment, then you see there is some frustrated positions periodically appearing, and you have two different periods, which is a kind of multiple to one another. Is called the bichromatic lattice. And there have been lot of papers on that, and interesting applications in 2008, where one observes Anderson-like localization in experiments, a sudden spike somewhere. So that was an emerging kind of very interesting observations. But then there was no theoretical aspects on that. So how it is and why it is observed, no explanation was existing in the literature. So we tried to give this approach first time that we started with. You see that the dynamical equations in the top is very non-trivial. We include all the terms which are space and time dependent. It is not to make the system non-trivial, but just to keep the more freedom with us. Because when we solve analytical equations, if we have a specific assumptions to start with, then it may happen that in the final solutions may require that assumptions which we have already eliminated. So that was the tricks we followed. So without getting afraid of the form of the equations and the answers and those things, you've started with the very general equations as much as possible for two-body interactions and loss gain and external trap. Then we have taken very general answer which is given in the middle, psi, expression of psi. No special form, no particular thing, but just amplitude and density part and a phase part, all are space and time dependent. So yeah, so when we, I'm not displaying all the things, but just to mention here that there are consistency equations and all of these have to be simultaneously satisfied. So we have to solve all of them, and then one can get a consistent dynamics corresponding to the particular potential. So here it is bichromatic lattice. So then finally, this is the solution. And the solution looks too much mathematical, but it is not. We directly connect it to the experiment through B1, B2, as you can see the arrow that, this B1, B2 is the intensity of the laser, both the standing waves, and L stands for the period of the lattice. So both are very easily tunable. Routinely people are doing in it experiments. But the interesting point here, unless you maintain a particular relation between the intensities and the period, you won't get a solitary wave. That's the point we are going to emphasize here. So we know which parameter can tune it. Only doing the experiment will not do it unless one correlates with the particular analytical results. So we mentioned about the tunability, that how one can tune bichromatic lattice to get a particular profile, solitary wave, of ultra cold atoms. So here are some of the kind of pictorial examples to get a bright soliton. The first one is the optical lattice. One can understand that it is a single kind of maxima for attractive interactions. But as long as you increase the intensity of the laser, the atoms, the BEC kind of able to see the potential profile. So it can see the minima and maxima. Then it tries to localize in the minima in the bound states instead of the maxima. So as you go on with this, then you get third plot, you get a frustrated positions, as I have already mentioned, that the other frequencies, other period is also kind of a significant here. And then you get a particular, you see just this, some intensity in the frustrated position starts appearing. So that is kind of an Anderson-like localization. And these are exact analytical methods. So it's a strong localization in the middle in a frustrated positions, not in the in a potential well. Optical lattice well is the frustrated positions. So that is the one which is observed in the Nature experiment in 2008. And there is some condensed fractions and other confirmatory things we have done. And this is the repulsive domain which nobody has observed so far. And you can see the backgrounds are kind of is modulated by this. And at the end, when I have a large intensity parameter, then I could have get a solitary trains using repulsive domain, using repulsive interactions. So that may be one good.
Utpal, do you hear us? Do you hear me?
No, I think
in this direction, the biochromatic.
Okay. Let's see. He'll hopefully come back soon.
Yeah, I am back.
Yes, you're back. Good. Now we can hear you. Yes.
Yeah. Okay. So this is the rogue wave, which we are trying to get it is the recent results. I'm just showing, I'll just show one or two slides about it because I have taken a lot of time for the network issues. So I'm of a non-trivial to solve, and in addition to get a rogue wave, one has to have Darboux transformation in a Lax square method, and then finally connect to the Manakov system, and then one can get a solitary excitations where there will be you will have the disappearing of the rogue wave in the system, and this is the we are analyzing more about it, but here I have just given one slide about it. So now one thing is that people have been doing the experiment for engineered lattice. So one can tune the lattice in experiments. Say if I want to get a particular profile, particular form of the condensate, one may need to change the frustrated depth. One may need to change the shape of the potential in a particular form. But how to see it from the analytical point of view? So for that, you need to have a more freedom on the potential. And so we have modified the BOL. You see, this is a very, the combinations of two BOL, and there are a lot of combinations between the frequencies could have been done. And in experiments, the interesting thing is that if one does the experiment without any theoretical knowledge, so the parameters, the intensity terms of the lasers will be taken arbitrary in the experiment, but it is not. If somebody takes it arbitrary, the solution will not be stable. One can get a BEC initially, see some maxima over there, then with time it will decay very fast. So that won't be a kind of a stable solution in the system. So a stable solution will be obtained only when one can have a particular relation between the intensity parameters. So here are some examples. You can see that the first plot is nothing but bichromatic lattice. Whereas from the second plot from B, C, and D, you can see there is a double well appearing periodically over there. So it is not only double well, it's a double well superlattice. In addition to that, you have disorder over there. And disorder in between the double well that is visible in plot B. In plot C, you also have a disorder in the smaller maxima of the double well. An interesting part here is, which is absent in all kinds of potential, is that your double well bifurcation in B plot, the bifurcation of the condensate is visible and they are separated. Double well is very important in quantum information science for the ultra-cold atoms, but here we are producing double well superlattice. And then the maximas and the bifurcations are separated. So it could have been a very good candidate for quantum information science. Not only that, in C plot, which is drastically different from bichromatic lattice, that we have a Anderson-like localization. In addition, we have separate maximas, well-separated maximas in plot C and D. So this is very different, and we could have we tried to think about the reason. What is the physical reason about it? Because multiple frequencies are overlapped here, and that may be the reason. But why? Then we looked at it in the phase space, and we found very interesting thing that instead of kind of getting a particular in BOL, we have seen that there is a particular maxima in the position, and there is a center is a strong maxima which is coming as Anderson localization. Where here it is not, we got a kind of butterfly shape condensate in the phase space, which says that in this background, non-zero background in between the bifurcations, that comes from the this maxima, which is continuously from one well to another, and which is disappearing with increasing the beta values. So one can actually tune the potential, engineer the potential. I'm just mentioning it very briefly so that I can give an idea about what is actually going on. But then there are a lot of parameter variations which we directly connected to the experimental parameters, and we can predict that what we actually are going to get it. So this is about the engineered potential for getting condensate bright solitary trains in superlattice with double well. Now this is the last part of my talk, which is the negative observation of negative temperature, which is recently we have found it that from the experiment of 2013 that this is the first time in any physical system one observes negative absolute temperature. So whenever we talk about temperature, we always understand that this is a positive temperature, and the temperature scale we have been using since years. But then here some experiment is first time observed in ultra-cold atom to achieve negative temperature. So what is being done is, it is the optical lattice superimposed on a harmonic potential, and it is slowly inverted. And if the atoms are localized in the higher state, remember that this is an equilibrium state, not like a laser, then it is possible to define it as a negative temperature. There is no other way. If we want to satisfy the distribution function, then we have to define the temperature which is negative. So that's the, that can be confirmed by entropy and momentum and a lot of other aspects. So we again, try to see this thing using our analytical method. We thought we won't get it, but then finally we could get it. And then not only got it, we have modified it to the optical lattice to bichromatic. And I'll tell you the reason why is that, to modify it. And you can see the expression of the potential on the top, which is, kind of, against the star. This is the expression of the potential. And you can see two different periods, which is 2L and L, and a lot of freedoms in the time-dependent parameters, so that one can tune the potential the way they want in the experiment. But what we get is, I'll directly go to this density. You see that density is localized in the frustrated positions. If you tune the laser parameter, I am able to accumulate the density in the frustrated position, which is a position where you can trap the condensate is a much more stability. So the negative temperature state will be obtained with a faster speed, it will be obtained quicker, and also it is more stable if one uses a bichromatic lattice instead of an optical lattice. So that was the modification. But yes, one case of this is optical lattice. This is a special case of our method, but bichromatic is the general one. So we have also shown the time, evolution of the state, how it moves in the space, and atom transports. So atom is transporting from one state to another at negative temperature. So tunneling and quantum information processing could have been, this, if one observes the interference terms in the phase space, as you can see in the density profile, it will be a very interesting profile, and we have observed that. We have noticed also that one, but I am not including it here. So this is a study which we have confirmed by kind of changing the parameter and estimating the temperature, and showing that what is the, yes.
So we have 19 minutes past. Go ahead.
Okay, I'll just take 1 more minute. That's all. Yeah. So I am almost done because I thought I have taken a lot of time to save some time. I have done it little bit.
Sure. Please go ahead. Yes.
So we have, so we have estimated the temperature here, and temperature is measured with respect to the parameter of the frustration. So as we increase the frustration parameter, the intensity of the laser and the period of the laser in such a way, the temperature can be tuned. So that's the important thing. You can see the parameter beta1, beta2. There are 2 parameters, and then entropy is, slope of the entropy is calculated, and we see that the stability is varying with the change in the frequency of the harmonic trap and the laser parameter, which is responsible for creating the optical lattice. So so this has just appeared in scientific reports here, and so the conclusion is that we have started with disordered lattice to address analytically that we have been solving the system optical lattice and bichromatic lattice to get a particular condensate density. It's not abstract mathematical methods. We are connected to the experiments, and all the parameters are experimental parameters to get a particular dynamics. And when you talk about the engineered bichromatic lattice, then we find that this is more interesting and more useful system that we are going to propose. And in addition, we have also proposed log wave and the observation of negative absolute temperature. So now this is my core family of my research family, my students. The negative temperature work is started by Ajay, and Jayanto has just completed. Jayanto is also presenting today. He will be presenting about some work which is going to appear in PR in few days. The observation of bees in ring trap. Then Nilanjan is doing about log waves. He has a lot of interesting results about it. And Borun is actually expert in engineered lattice, and he's also looking at the phase space quantum information about it. Then Abdul, Vivek, and Prados, I have not mentioned about their work here because they are working in a little different things. So I would like to thank for listening to me and bearing with the technological problem of the network. Thank you.
Thank you very much for the nice talk, despite rogue internet waves. Yeah. So if there are questions, please do raise your hand. But meanwhile, let me just quickly ask you a question. So I was confused about the solitron profiles that you were showing. Okay. Are they steady state wave functions that you were showing, or do they actually move coherently in time?
Okay, so the initial solution which we showed for bichromatic lattice, and that was a steady state solution, is a time independent solution. The time evolution, when we find the steady state solution, that means that one can observe the time evolution after that, but we are actually just mentioning the steady state. One can change the system parameters and one can see the evolution. But the negative temperature case and a part of the engineered potential, there we have shown the time dependence of the condensate profile, but that is also starting with the steady state solution.
So just the related question there. So yes. the potential, if the potential itself is time dependent, then what do you call the steady state? It's after some protocol, the state that you get is a steady state?
Yeah, so actually, we are giving enough. So how the experiment in condensed is being done. So I'll show you a particular plot about the negative temperature here. Say in this case, imagine that I have a potential in the beginning, and then I get a steady state for a particular potential parameter. Then when I change the parameter experimentally, what people do is they are doing it very slowly so that the system gets a time to come back to the steady state again. But it is a different state from the initial one. So they actually observe in the experiment is a snapshots at a particular time, and that is what actually. But analytically, we are able to plot it and continuously. But in experiment, it will be only snapshots.
Thank you.
Yeah.
Ganesh, I have a quick question, if I may ask. Sorry, I cannot raise my hand as a host. Okay. So just to understand, so how are you characterizing the disorder, in the sense, maybe I missed this.
Okay.
So for example, if I say disorder of a certain strength, how does one characterize it within your calculation?
Yeah, I'll show you this. I think this slide will be. Yeah. So here. You can see the potential profile in the middle of the slide, where
yes.
Bichromatic optical lattice potential is given, and in blue we have designated V1 and V2.
Oh, I see. So you're using
so
that.
That's the intensity of the laser. Two standing wave. That optical lattice is created by two counter propagating laser, yes. One optical lattice. So here it is two.
Yes.
But in addition to that, and there is a L, which is the period of the lattice.
Yes.
Okay, and then after that, what we are saying is that it is not that B1, B2 and L1 and L can be taken arbitrarily. It is not like that. So if somebody wants to get a stable solitary wave, then one has to have this particular relation of B1, V2.
Yeah, I guess I was contrasting between the usual notion of Anderson localization by disorder, and this seems to be some kind of a quasi-periodic. So there is no variance, is it? In terms
no,
of
it is. So my opinion is, in that paper, in Nature paper, they have mentioned about Anderson localization, but I won't say that this is a Anderson-like localization, which appears in a kind of continuous variation of a system parameter and localized in a frustrated position. So it is more about a strong localization in the frustrated position. That is the kind of the phenomena which is correlated with Anderson localization.
And here in this picture, for example, the strong localization. Yeah. So what is the notion of frustration? I'm sorry, I probably
yeah, no problem. Yeah. So if you see from the first plot to the fourth plot, then this beta parameter, which is related to V1 and V2.
Yes.
Okay, so if so that is the parameter which is controlling V1, V2. So that is why we have mentioned beta over there. If you change it, then the frustration in the potential comes. So these line plots are for the potential, and field plot are the density.
Yes.
Okay. So initially it was optical lattice, and slowly it is getting a disordered minima in between the main minima. So that is the kind of a frustrated position we are talking about. And
disorder,
yeah.
I'm sorry. I mean, this is not.
Anumitra, could we?
Yeah, sure. Please, maybe I'll talk to you
later. Offline. Yes. So we are already running late. But thank you. Thank you so much.
Okay.
Thank you for the nice talk.
Yeah.
So hopefully no more rogue waves. Yes, I mean hopefully lots of rogue waves in experiments and papers, but not in conferences.
Yeah.
Good. So let's invite the next speaker, Manas Kulkarni. So Utpal,
I'll just unshare my
stop
screen.
Sharing your screen. Yes.
Yeah, sure.
So the next speaker is Manas Kulkarni from ICTS.
Hello.
Hi, Manas. Yes.
Hi. Okay,
so as soon as Utpal stops sharing, yes, good. Here you are. Yes, good. So I'll remind you after 19 minutes, but please start. Over to you.
Sure. Okay. So first of all, let me start by thanking the organizers for inviting me to give this talk. It's very nice that this conference series is continuing. So today I'm going to speak about basically two stories. One is localization and one is quantum state transfer. So basically this talk is going to be divided into localization in cavity QED network, and the second part will be on quantum state transfer in a cavity QED network. And here are the references, and this work is done with Amit Dey, who was a postdoc at ICTS. So let me go to part one. So let me give you a quick overview of the system of interest. So if you see the screen here, we have what I call one unit. One unit is basically a Jaynes-Cummings model, which is a cavity with a qubit. And then you have bunch of these units, and each unit is coupled. The cavities are coupled with each other. So the fundamental unit is the Jaynes-Cummings model, and there are two types of dissipation. One is cavity dissipation, and another is qubit dissipation. And there is also a drive. There is also a drive given by D1 here. Okay, so this is basically the system, and the unit here is given here. The Jaynes-Cummings model is just a cavity and a two-level system, and a cavity coupled with the qubit, and G is the interaction. So this Jaynes-Cummings model in itself has several interesting regimes. There's one regime called dispersive regime, where this so-called detuning, which is the difference between cavity and qubit frequency, if it is far greater than the light matter interaction, then you can map the system to a weak Bose-Hubbard model. On the other hand, if you are at resonance, then you basically have strongest anharmonicity. So now the question is, if you take this Jaynes-Cummings model and then you couple them, you couple many of these Jaynes-Cummings systems, and via this J coupling. Okay, so again, here is the diagram which was there in the previous plot, previous slide. So you see the Hamiltonian is now you have this each of these Jaynes-Cummings systems with some details, with some additional details. But the important thing is there's a J which couples the cavities here, J, AI dagger, AJ. And I told you that there was dissipations. So one can basically solve for the system using Lindblad master equation, and the quantities of interest that we are after are this expectation value of A dagger A, and let's say expectation value of the spin operator. So I will mostly focus on expectation value of A dagger A. So now the question is, what are we interested, and why are we interested in this? So we'll be after this quantity called population imbalance, where you can imagine that every odd cavity is initially populated with photons, and then you let it evolve in time. So basically what happens is that once you let it evolve in time, initially the imbalance is basically by this very formula is 1, and then if it remains self-trapped or localized, then the imbalance will stay close to 1, or it will at least be finite. But then if the photons start moving all over the place to the empty regions, then imbalance will might even go to 0. So imbalance is a very good diagnostic for giving an idea of localization or self-trapping. Okay, so why are we even interested in this? So in fact, a simpler version of the setup has already been realized at Princeton a couple of years ago, where the experiment had no additional drive. So it was more like a Hamiltonian system, but they were, of course, unavoidable dissipative effects. And they indeed saw that there is an interesting sort of phase diagram where you can have parameter regimes in which the system gets self-trapped, and everything is because of that nonlinearity, which is the G, which is the light matter interaction. And there is an interesting phase diagram where there are regimes where you end up getting delocalized states and so on. But notice that there was no drive. But then the question is, what happens if you have a drive? Because if there's no drive, eventually, no matter how interesting the system is, the cavities will become a vacuum and qubits will go to the ground state. So in some sense, if you have unavoidable dissipative effects, but then you can ask, can I drive this system in such a way that you end up with self-trapped states? And it turns out that it is not that trivial, because because of what I'm going to explain later. So the central question is how to sustain indefinitely, how to sustain this self-trapping indefinitely. And also there are experiments where the model has basically been realized for large-scale system. For example, here is what is an experiment at Princeton where they have 72 units. So basically, there are a lot of these many large-scale engineered setups where one could ask such questions. Okay, so now let me go to the results. So basically, we can either solve this Lindblad quantum master equation either by traditional methods or by quantum Monte Carlo wave function method. But let me explain this plot a bit. So here is the imbalance, and this is 2 units. Okay, so here imbalance is basically left minus right by left plus right. So here you see that when you don't drive, and this G1, G2, these are all light matter coupling. So this is the interaction. So you see that for a while, it is actually self-trapped. But then because of dissipation, it just dies away. On the other hand, you can have situations where you drive, but still it doesn't really work. And you see that drive is basically, it is able to sustain it, but then it is basically going away again. But then this is a slightly, there are a lot of parameters in the problem. So if you sit at the right, parameters, you can realize a situation where you drive and basically you have indefinite imbalance, indefinitely sustained imbalance, which means that this is just infinitely, for infinite long times, it is basically trapped so when n is equal to 2, I start with a situation where there are initially there are photons maybe in the left cavity, and then it turns out that they just get trapped. You can ask similar questions for n equal to 4, and these are quantum calculations. And here you see that when there is no drive, the imbalance is basically lost. But when there is drive, the imbalance is basically 1, almost 1, which means that it is almost perfectly trapped. So the main observations here are that for sufficiently large light matter interactions, G, so G1, G2, G3, G4, there is indefinitely long-lived self-trapping or localization. So there is a very delicate interplay between drive, dissipation, light matter interaction. What I mean is that there is an optimal window of drive strength in order to achieve non-trivial steady states. Meaning that you just cannot drive thinking that, oh, I can, you cannot overdrive it, because when you overdrive it, you might end up reaching a situation where you lose the self-trapping. So you might leak out to the empty units in some sense. So there is it's a complicated story with so many parameters and interplay. And then you get self-trapping even if couplings are uniform and so on, which means that there is it's a truly interesting phenomena where there's a large parameter space where there is self-trapping. Okay, so now let me just go to the semi-classical version of this problem, the same model, and there we basically can do 100 units. Basically, these are the semi-classical equations, and if you see the lower figure, you see that there is a critical GC, which is given here, where if you're below the critical GC, you lose imbalance. If you look at the inset here, but if you are at 2 GC, then if you're less than 2 GC, you lose the self-trapping. But if you're at 2 GC, you have imbalance. And this is the closed system. So there is no drive and no dissipation. And here it's a driven dissipative system. So here you see that when I have my drive in certain region, I get one imbalance of 1, which is perfect self-trapping. But when the green is when there is no drive, and this little basically blue line is when it's overdriven. So basically what happens is that when you overdrive the system, it is actually not good. So basically, you can think of some phase diagram of this sort, where you have this regime 1, which is underdriven and so non-self-trapped. Then you have a regime 2, which is appropriately driven and indefinitely self-trapped, and regime 3, which is overdriven and delocalized. So basically, if I pick a particular kappa over j and go this way, then I see that if I drive it too much, I lose the self-trapping. So conclusions for part 1 are that there are interactions which are crucial for this self-trapping. There's a delicate balance between interactions, drive, and dissipation. There's an optimal window of driving, and localized self-trap state is independent to initial conditions. So this is one important point, because this is a driven dissipative system. We often have a unique steady state, and so it doesn't matter what is your initial condition, which is experimentally very useful, because you don't have to bother about making very fine-tuned initial conditions. And we also compared the open and the isolated systems. So as outlook, there are possible experimental implementations of our predictions, which we are discussing with some experimentalists. And there's development of theoretical techniques to study this many-body localization, which we are working on. And also there are various lattice geometries, which is a very active field. There are papers, experimental papers, and there are some mathematical physics papers, and various networks where one could ask this kind of localization in these non-trivial networks. So let me go to part B. So part B is philosophically almost opposite of self-trapping. So here we talk about actually quantum state transfer. So now, by now, this diagram might have become familiar. So we have a similar diagram here. There are slight differences where this coupling now between the cavities, this A dagger B and B dagger C, this is time dependent. And basically this is the Hamiltonian. It's a Jaynes-Cummings Hamiltonian with time dependent couplings, and interaction is G. So now let us work with the very trivial limit, that is the linear regime. So when G is just 0, when GAB is 0, when G is just 0, this is just 3 harmonic oscillators, right? So one can see that this is an eigenstate, and this eigenstate basically acts like a dark state in the sense that it doesn't project onto B. However, if I change J slowly, which I can do, I can go from A to C, which means that I can, in principle, if I slowly evolve the system, I can go, I can transfer photons from A to C with almost minimal occupation in intermediate cavity. And this is often called the Stirrup scheme. And one quantity of interest here is the transfer efficiency, which means that given I have a few number of photons in the first cavity, what is the efficiency which I get photons in the last cavity with almost zero occupation in intermediate cavities. So one can ask the question, what happens to interacting or nonlinear cases? So just to recap, the idea is to transfer photons, for example, from A to C such that throughout the time dynamics, there is almost no occupation in B. So you see that there is a non-trivial pulse sequence here, which needs to be activated. So now the question is, to answer this kind of question for interacting systems, we actually first go to the classical version of, semi-classical version of the problem. So the procedure is slightly complicated, but let me give you a flavor. So the idea is that there's a particular parametric time, Hamiltonian parameter, on the x-axis, and here we can plot the compute the stationary point solutions. And the idea is that you pick the special stationary point branch where you see that you can go from A, where NA goes from some 20 to 0 and NC goes from 0 to 20. And you sit on this special branch, and then you basically try to follow this branch during the real-time dynamics. So in the real-time dynamics, if you slowly evolve the system, then you see that these red ones are when you have fast sweep, blue ones are when you have slow sweep. So red ones, you see, if you have a sweep, then you basically manage to go from 20 photons to 0 photons in the first cavity and 0 photons to 20 photons in the last cavity. The blue one is slow sweep, where you see that it did not do very well because it is passing through some chaotic window, which I will explain. So basically, on one hand, if you want to adiabatically follow, you should go slowly. But on the other hand, if you go too slowly, you are going to spend more time in the chaotic window, which might be bad for your dynamics. So there is some complication between adiabaticity and chaos, which means that upon slowly varying the parameter, the system remains in the Hamiltonian instantaneous state. So in this case, it remains on the special branch. But this implies that sweep rates cannot be too fast, because then you are unable to adiabatically follow. But on the other hand, the sweep rates cannot be too slow, because then you pass through chaotic regions. So these vertical lines that you see here, these are chaotic windows, which is what I will explain in what follows. So the idea is that you have to make sure that you have to choose your sweep rate such that you are able to surpass the chaotic regions fast. At the same time, you don't do so fast that you jump onto some another branch. So that is the delicate optimization that you have to do. Okay, so now coming to the chaotic window, what does it actually mean? It just basically means that for a particular parameter in the Hamiltonian, this is just particular parameter Hamiltonian, you can compute the Lyapunov exponents, and then you see that there is a regime where let us just focus on this GC or 0.1, for example. GC, this is light matter coupling, and you see that there's a window in which the Lyapunov exponent is positive. This basically means that that is the window where the system can be chaotic. So this gives us the vertical window that I showed in various plots. And you see that if you have strong light matter coupling, you see 0.1, 0.2, 0.4, you have more chaos. So in this figure, we can basically use this information to calculate something called this efficiency. And here it basically says that you cannot be too slow, nor you can be too fast, so that you have efficiency of almost 95%, which is considered satisfactory in the community. So the idea is that how do I sweep my pulse so that I can, with significant efficiency, reach my desired final state. Okay, so now this is my sort of almost last slide, where one can scale up the system. So you see here, these are 4 units. So you can see Na, Nb, Nc, Nd, and you see interestingly that Na goes from 20 photons to 0 photons. Nd goes from 0 photons to 20 photons. But Nb and Nc basically barely have any photons throughout the time dynamics. So there's a perfect quantum state transfer between the first cavity to the last cavity, and throughout the dynamics there is very little photon occupation in the intermediate cavities. Here is in the last plot we did a semi-classical quantum comparison. So notice that I spoke about semi-classical calculations. This is to get an idea of where the Lyapunov exponents are positive and where is the chaos regime and so on and so forth. But in the end, one can do a quantum calculation after getting an idea of what is the right sweep rate. And then this is a comparison between quantum and semi-classical. And you see that the solid lines here are quantum and the dotted lines are basically classical. So you see that there is almost a perfect agreement between semi-classical and quantum here. And you see that the quantum also, this is basically quantum calculation. So all the solid lines here are quantum and these dotted are semi-classical. And this is when there exists a chaotic window. This is a situation where there is no chaotic window, meaning if there's no interaction, there is no chaotic window. Okay, so this is the final conclusion. So we demonstrated in part B something almost philosophically opposite to part A, where we demonstrated a protocol for achieving high transfer efficiency in an interacting system. And this is far from obvious, especially since we are dealing with a scalable interacting system. And there is a deep connection between Lyapunov exponents and these stirrup schemes. Successfully achieved our target for the fully quantum case. And we also considered various initial states like Fock states, coherent states, cat states, and so on. As an outlook, we are trying to adapt and extend these protocols in different fields where a variety of engineered Hamiltonians are achieved. So these Hamiltonians are highly engineered and tunable. And there is some ongoing work with optomechanical setups. And some quantity that was discussed in this conference was OTOC. And one fundamental question is trying to study the OTOC and do further investigation on Lyapunov exponents in our Hamiltonian setup, because our Hamiltonian has both chaotic and non-chaotic regimes. So it's a nice platform to study OTOCs and so on. With that, I thank you for your attention.
Thank you very much, Manas. Thank you for the nice talk. You had a very memorable, inspirational quote. Without drive, eventually everything will become vacuum. So I will remember that for some time. If there are any questions, please do raise hands. Meanwhile, let me just ask a quick question about your part A. So I didn't understand the network structure. So you're saying the drive comes from the left, right? And then you have, say, n cavities.
Right.
What happens after the nth cavity? Is there periodic boundary conditions, or is it just open?
No. So here technically you can drive every cavity. Okay. So what we do is we drive for example, we drive every alternate cavity. Okay. So and this is just the first unit, and this is the last unit. No periodic boundary conditions.
I see. So it's like,
but the important point is,
yeah, I think I understand. I see. So they're all being driven or alternate.
They're alternately driven, but then even if you alternately drive it does not guarantee at all that you can have self-trapped states, because let's say I drive the first cavity, because of excess number of driving, photons can just leak out to the second cavity and destroy self-trapping. So there is a complicated interplay there.
I see. Yeah. Good. Okay. There are no other questions, so let's thank Manas. Thank you, Manas.
Thank you.
The next speaker.
Thank you.
So the next speaker is Jayanta. Jayanta is online. Jayanta, please do share your screen.
Shall I share my screen?
Yes, please. Okay, so speaker is Jayanta Bera from IIT Patna. So Jayanta, I will remind you after 8 minutes. Please to start. Over to you.
Thank you, first of all, to the organizers for giving me the opportunity for presenting my talk here. So in this meeting, I am going to discuss matter of fractional revival in ultra-cold atoms. So I am from IIT Patna. So I will start with very brief introduction about the Bose-Einstein condition and application. So Professor Roy already said this, but for the completeness, I am going to talk very briefly. Then I will directly come to my result. This is the listed of the outline, but I am going to talk one by one sequentially. I will first start with the proposed model, then I will explain some dynamics. Basically, this will be the all numerical work, and after that, I will explain some theoretical analysis of this result. Then I will tell the both numerical and theoretical analysis for the comparison or for the completeness of my talk. At the end, I will complete my talk with a concrete conclusion of the overall talk. So, what is the Bose-Einstein condensate? Bose-Einstein condensate, which is the state of matter below certain critical temperature or nearly absolute 0 K, when all the atoms occupy their lowest energy state. This is the basically boson when at the nearly 0 K they come to the ground state and they form a giant macroscopic matter wave. This is the state of fifth state of matter or boson state condensate. This is the first. This is the false picture of the momentum distribution. If we go to this direction, this is the lowest temperature. This is the nanokelvin temperature when the momentum distribution. The most of the particle is the ground state where the momentum is nearly zero. So the sharp represents the Bose-Einstein condensate. So what is the dynamical equation of for this Bose-Einstein condensate? Actually, if we use the mean field approximation and second quantization, after some derivation, we can reach to this the final dynamical equation. This looks like the this is the nonlinear Schrodinger equation. Here the two term basically. This term is coming from the interatomic interactions, and this term is the external potential. These are the two major terms in the dynamics of BEC, which control the shape as well as the dynamics of BEC. Where phi is the condensate function here. This equation is called here as a Gauss-Krivitsky equation. So what are the applications? There are many more applications we know from starting from the matter wave interference to the atom laser to the atomic clock, and there are many more applications. Here I am showing the one most recent or experimentally observed BC in space, in orbiting space, which is the published in 2020. This is this, and the other some important application is the negative temperature. I think Professor Roy already said, and I am going to tell here BEC in a toroid where we will observe the fractional revival phenomena. This is the first experimentally observed toroidal kind of trap. What was the by S. Gupta? This is the experimental result, and there are some other application approach which I am going to explain here. So coming to my work, what is fractional revival and fractional revival generation alpha atom in ring shape trap. Here is you can see this picture in the top here. This is the one wave function at t equals to 0. This is the spatial distribution, and at t equals to 3 fractional by 2. This is called half revival. When the wave function 2, its profile looks like same, but the spatial distribution, if you look the spatial distribution, it's opposite direction. So it is called the revival of this wave function at t equals to 0. But if we do the autocorrelation, basically if we do the superpose, then this will goes to the nearly 0. So though it's revival pictorially, but its autocorrelation can goes to 0. So now what is the actually definition of the fractional revival? Basically in quantum mechanics, if a quantum mechanical wave propagating in with time, if the periodic recurrence occur, then it is called the revival. Sometimes a fraction of time periodic can occur, then it is called the fractional revival of the wave function. So now coming to the model, what we consider here, we create a toroidal kind or ring shape potential, which is created by the harmonic trap, two-dimensional harmonic trap. This is and a Gaussian peak at the center. This is the Gaussian peak at the center, and this is the dynamical overall total dynamical equation. This is the dynamical equation. Here we can see this is the Gaussian peak, and this is the harmonic trap. And initially we place a BEC in this minima of the ring trap. You can see we place here on BEC. If we look from the top view, we can see this white line. This is actually the ring kind shape, and this blue one is the BEC we place here. If we look at two potential are present in this system, but BEC will propagate along the y direction where there is potential almost 0. So this will be the almost free propagation. This will be the along this direction. This will be the free propagation, and this we call as a waveguide here. So now if we see here, initially if we look at this picture, initially we start with a BEC from here, then it is time evolution, it is expanding along both directions and coming in, they are colliding here and create this interference pattern. And you can see this is creating the interference pattern. Almost same kind of phenomena, this interference pattern already observed in this experiment. This is the experimental paper they observed, but they didn't observe. If we do for long time, you can see these petals are coming and this number of petals also increasing and decreasing with time. You can see if I increase the time, you can see this number of petals 5, and here this is the time. And another interesting thing, if we go to the, if we go coming to here, when we can see that the yeah, you can see the initially, though we initially started from top, the all the condensate coming at the down at this time, and if we increase more time at the end, we can, I'm going to first a little bit, yeah, you can see again all the condensate going to the top. So the pattern is the density periodically reviving, and some fraction of this pattern, similar pattern, is coming with time. You can see at the time t equals to 2.37 seconds when the condensate is revived. We call this time as a revival time. Now, if we take the snapshot at different time, where we plotted here, showing here, here we can see at I'm going at 2.37 second. I said that this was the revival time. If we divide by 2 this revival time at the half revival time, you can see this. Sorry, this will be the this time when we can see these are the this is the condensate. And if we do revival with 4, 8, and this time, we can see this time, this type of density distribution. If we divide the revival time with 8, then we can see the 4. If we divide it by 10, revival time with 10, then we can see the 5 number of petals, and if we divide by 12, this many number of petals we'll see. So if we want to see how many number of petals will come at what time, just by dividing the fraction. If we know the revival time, just by dividing the number with some number, then we can get the how many number of petals at what time this will come. So now coming to this, this F1 is the phase distribution. This corresponding to the figure.
You're 8 minutes past. Go ahead, please.
Yes,
8 minutes past. Please go ahead.
Okay, sir. And this is this will be the phase distribution. We can see for this, for these two, this is the blue line, and this for red one, this is the, we can see though they look patterns are symmetrically, but their phase distribution are different. So now coming to the autocorrelation function, if we do the autocorrelation, we can see this red one line, which is for one. At various times, these spikes are coming. Each spikes corresponding to a fixed pattern distribution, representing the pattern distribution, and this number corresponding to the number of petals. So if we calculate this time, and as present in the theoretical in the mathematical form, this will be the in the form of TR by M by N. Where S will be the here S is actually represent the petal number. So if I want to know the number of petals, just putting the numbers here, we can calculate what will be the time or how many petals will come. So coming to the theoretical aspect, as I said, the two waves coming from opposite direction. So that's why we consider the two waves and propagating waves. If we do the interference analysis, we can see this will be the interference term, or this is the separation between the two petals, and from this, following this step, we can come to the T revival time, which is actually R0. Here R0 is the ring radius, which is proportional to the R0 square. Actually this result, this similar kind of result, similar kind, in this work they also propose the revival time in toroidal case will be proportional to the R square. So numerically we also verified this, numerically calculated the revival time, and theoretically calculate the TR, and we match this almost quite match the result. As we know that for all numerical result analysis, stability analysis is quite important. So we also done the stability analysis. We check that the error is very less, for even by adding the 50% noise, 5% noise to the initial wave packet. So these, and I coming to the conclusion part. We started with the BEC interference. If I observe the BEC interference in ring sector, and first then we observe the fractional revival, which is very new in this BEC in recent time, and the phase information, which is also quite important. And this model is quite useful for quantum measurement, also in quantum measurement, quantum metrology, even in the quantum gates also.
Thank you for the nice talk, Kenta. Are there any questions? Let me ask a quick question. So how much of what you're saying depends on the form of your initial state, right? Your initial wave function, is it a delta function or it's a Gaussian, right? You said
initially it is the Gaussian function. Then we add the noise, random white noise actually with 5% of the initial peak height. Actually, experimentally, there may be chance of presence of noise. That's why we consider if we add some noise, then this revival time will come, or this autocorrelation peak will come properly. So then we observe that it is coming properly.
No, but initially, suppose you had taken a delta function instead of a Gaussian.
No, actually, taking the shape, it's depend on the, since we are creating initial shape, what was the creating the potential, this is the harmonic profile, almost harmonic profile. So in case of harmonic profile, the solution initial PEC solution, or basically the solution harmonic potential solution comes as a Gaussian.
That's true, but you're anyway putting it in a different trap, right? I see your point. So it's easier to make a Gaussian, so you make a Gaussian and then you use that as initial state. Right? That is what you're saying. Okay, good. Okay, thank you for that answer. Are there any other questions? Okay. If not, let's thank Jayanta and let's go to the next speaker, Devottam Mandal. Thank you, Jayanta. So, Jayanta, please stop sharing your screen and Devottam can share his screen.
So, hi everyone. So, visible the screen, right?
Yes. So, Devottam Mandal from IIT Kanpur will give the next talk. So, please start. I'll remind you after 8 minutes. Go ahead, please start.
So, yeah. So, hi. Welcome of physics. So, I will talk about Magnus-Nernst and Magnus-Thermal Hall effect. So this work has been done in collaboration with Professor Anand Kumar Agarwal and my senior. So ordinary Hall effect, as we know that if we apply a current in a sample,
By internet. Okay, let's see if he logs back in.
Hello.
Devottam, can you hear us?
Hello. Yes.
Hi.
I can hear. Yeah. Sorry, I get.
Sure.
So as I was saying, so ordinary Hall effect. So
please share your screen again. Your screen is not shared. Devottam, you're on mute now, and your screen is not shared.
Hello.
Hello. Hi.
Yeah. So is it visible on my screen? Shared actually?
No, I don't see your screen. Perhaps your internet connection is not strong.
Yeah, looks like the internet connection is fluctuating.
Should we move on to the next speaker, and then Devottam, meanwhile, you can try to see, maybe switch to another internet connection if you have one.
Devottam, maybe if you want to take a few minutes, we'll have the next talk first and then come to you. Oh, he's already trying to share. Let's see.
Hello.
Okay, yeah. Yes,
Yeah,
hi.
so
We can see your
is
screen
it
now.
visible right now?
Yes,
Oh,
it is visible.
sorry,
Yes.
there was a
Okay, go
network
ahead.
problem. I changed the network. Yeah.
Yes,
Thank
go
you.
ahead, please.
Yeah.
Continue.
So as I was saying, ordinary Hall effect, it is just the appearance of a transverse voltage when we apply a charge current and a perpendicular magnetic field in a sample, and it is basically due to the Lorentz force acting on the charge carriers. So, but in absence of magnetic field, also you can have a Hall effect if there is a finite Berry curvature present in the system. So, Berry curvature is just a geometrical property of the quantum states of the system, and it actually plays a role of effective magnetic field in momentum space actually. So which is known as basically quantum anomalous Hall effect. Now whether it is the Hall effect is due to magnetic field or due to Berry curvature, it is generally seen that Hall effect requires the time universal symmetry to be broken actually. So which is and it is due to the orthogonal component of the conductivity matrix sigma xi that is 0 in presence of time universal symmetry. That's why we need broken TRS. So the question is, can we find any Hall response in time universal invariant systems? And so the answer is yes. And it is in and in this direction, there is two way. One is the nonlinear Hall effect, which is second order in the external electric field, and that there is quite a lot of work on nonlinear Hall effect present. But today we focus on the Magnus Hall effect, which is also Hall response in time universal symmetric systems. Now the specialty in Magnus Hall effect is that it is linear order in the external electric field. But here is a new kind of electric field also present in the system, which is the inbuilt electric field, which can be applied by some gate voltages in the system. So Magnus Hall effect is very recently predicted in 2019, and we extended the thermal and thermoelectric counterpart of this Magnus Hall effect in our systems. So elaborately saying, let's look at the picture here. We actually apply a electrochemical and slowly varying electrostatic energy in the this rectangular slab geometry, where this electrostatic energy variation sets up a inbuilt electric field grad U in equilibrium, and so equilibrium means here in presence of grad U also there is no charge current or heat current is appearing in the system. So this is because in presence of inbuilt electric field there is the chemical potential is throughout constant, that is mu bar in the system, although the energy of the carriers can be varying. Now additional to this inbuilt electric field, when we apply the bias, the external electric field or the external thermal gradient, then we see that there is a chemical potential asymmetry in the system. Now and due to this asymmetry, the carriers move from higher chemical potential towards the lower chemical potential in the sample. So now here comes the Magnus Hall phenomena arising, where these carriers are moving under the external bias longitudinally, that is along the length of the sample. Then the finite Berry curvature of the system interacts with the inbuilt electric field grad U, so that a grad U cross omega, the Magnus velocity, this is generated, and this triggers the particle in vertical direction in the sample, and this gives rise to the Magnus shift or like the Magnus Hall current in the system. So it is necessary to have finite Berry curvature in the system, and we will see that as we are seeking time universal symmetric systems, so we have to break the inversion symmetry of the system to have finite Berry curvature. Now, after knowing how Magnus currents are appearing, Magnus Hall currents are appearing in the system, we will see how to calculate the Magnus Hall current. So as usual, we calculate the heat current and the thermal current as a product of R dot, the velocity of the charge carriers. F1 is a non-equilibrium part of the occupation function, and there is dispersion of charge according to whether we are interested in heat current or in charge current. So for the velocity of the charge carriers r dot, here we clearly can see that the Magnus effect grad u cross omega is reflected in the velocity of the carriers. Although we assume in our work that the inbuilt electric field will not with a distribution function f. For the occupation function f1, we use the Boltzmann equation under relaxation time approximation, and from there we obtain the f1. Then we explicitly calculate the Magnus Hall currents and obtain the corresponding Magnus Hall conductivities as follows. So here we have calculated both the charge Magnus Hall conductivity and thermoelectric Hall conductivity and thermal Hall conductivity in both ballistic and diffusive limit. Now the charge conductivity sigma Bm, that is actually previously predicted in the first Magnus paper, and we calculate the other thermal versions of this conductivity in our paper. So the details of this expression can be found in this PRB 10220511414, which is recently published. And so what is special in this conductivity is that we can see that the conductive Magnus Hall conductivities are linearly proportional to the del U. Del U means which is a signature of the inbuilt electric field, and it is also depending on the Berry curvature in the system present, and it's basically a Fermi surface property, which is assured by the derivative of the Fermi function. So F EQ in the expressions are just the Fermi distribution function. And then after calculating this expression explicitly, we now move to different kind of models or systems in which we have predicted the Magnus Hall conductivities. So first one is that gap graphene system, which has isotropic energy dispersion. So in gap graphene system, it is there is a band gap delta, which breaks the inversion symmetry, which is necessary to have Magnus Hall phenomena. And when we calculate the
8 minutes have passed. Please go. So 8 minutes passed now. Go ahead, please.
Yeah. This when we calculate the Magnus Hall conductivities in each valley, we see that it is again linearly proportional to the band gap delta, proportional to the del U inbuilt electric field, and it is quadratically inversely proportional to the chemical potential. So we can say that yes, in each valley it is non-zero, but when we sum up over the Brillouin zone, then the total Magnus Hall response will be 0. And this is an important feature because we have taken an isotropic system. As we will see, in an isotropic system, it will not be 0 in individual valleys. Now, the Magnus Hall response is 0, but we can still find the Magnus Valley Hall effect in a gap graphene system, very similar to the Valley Hall effect, as we know. In the Valley Hall effect, basically the opposite Valley carriers with oppositely oriented Berry curvatures accumulate at the different edges of the sample, so that we have a different Valley accumulation in the edges. Similar kind of phenomena can happen for the Magnus Valley Hall effect. Actually, now moving to the next system, moving to next anisotropic system. Actually, this is monolayer WT2, in which it is an anisotropic system actually, and here we will see that the Magnus Hall coefficient is now non-zero, and we actually plotted them both numerically and analytically. Now the red and blue colors are just shows that there is a well match between the numerically obtained results and the analytically predicted results. And in the plots, we see that in each plot, the Magnus Hall coefficient is peaked around mu gamma. So mu gamma is that chemical potential in where the Fermi surface turns into a single Fermi surface from two disconnected Fermi pockets. So here, near the mu gamma, we see a pronounced Magnus Hall response, and also we see that deep down in the valence band, the Magnus Hall responses vanishes, which can be explained in the way that Berry curvature also get lowered deep down the valence band. This is monolayer WT2, and another anisotropic system is bilayer graphene. Now this is as it is anisotropic, we will see that here the total Magnus Hall response is non-zero, unlike the gap graphene system. In bilayer graphene system, also the Baker curvature is asymmetric in magnitude and orientation in individual values. So for bilayer graphene, we have plotted again sigma, alpha, and kappa, the charge conductivity, thermal conductivity, and thermal conductivity for two different temperatures. And for higher temperatures, we can see that it is deviating from the Mott and Mott relation, and we have time slow. So
please
we basically
please wrap up soon. You're almost out of time.
Yeah. So we calculate. So we plotted. Yeah. So so these are the three systems basically for which we have predicted Magnus Hall currents, Magnus Hall conductivities. So to summarize, here are the key points about Magnus Hall effect is that Magnus Hall effect is seen in time domain symmetric system, but to have a finite Berry curvature, we have to find Magnus Hall effect in Magnus Hall and Magnus Nernst effect in space inversion broken systems. Second thing is that anisotropy plays an important role because all the maximum plots and calculation we have done we are in ballistic limit, but when we calculate in diffusive limit, we see that in absence of anisotropy, at individual values, the Hall response, Magnus Hall response vanishes. So we have to make sure that anisotropy is present in the energy dispersion. And third thing is that Magnus Hall effect, although it is linear in external electric field, it can also think it as a nonlinear Hall effect, as a coupling of between the external bias and the inbuilt electric field is seen here. So that's all from my side, and I am really grateful to my supervisor, Professor Amit Kumar Agarwal, my colleague Kamal Das, other colleagues at Department of Physics, IIT Kanpur, and other IITs, and also I am thankful to Department of Physics, IIT Kanpur, and to the organizers specifically to provide me an opportunity to present here my talk.
Thank you, Dev. We're already running well past time. Are there any quick questions? Okay, so I don't see any questions. So thank you, Devota. Thank you very much. Please stop sharing your screen. And the next speaker, Paramita Datta, can share her screen now. Paramita, hi.
Hi.
Do you hear me?
Yeah. Am I audible?
Yes, you're audible, and I can see your cursor too. Go ahead.
Okay.
Over to you. So I will remind you after 8 minutes.
Okay.
Please start.
Thank you very much for the introduction. And I would like to thank the organizer for giving me this opportunity of this contributing talk. And myself, Paramita Datta, I'm from Uppsala University. So I will be talking about the Josephson current mediated by odd frequency equal spin triplet pairing on the surface of well nodal loop semimetals. And we'll be sharing a very few results from one of our recent papers with my host, Annika Blacksheffer. Yeah, the title is relatively long actually. So let me scan the keywords from the title and proceed step by step. So I will be starting with a prototype example of Josephson junction. So what happens or when we think about the two superconductors separated by a normal metal, and I'm talking about the BCA superconductor. So we have this A-square spin singlet, that is the up-down minus down-up. And we all know that the Cooper pairs in a superconductor, they are in a coherent state with a particular phase. And due to the phase difference between these two superconductors, actually the Cooper pair will mediate or penetrate through this normal metal and carry the current. So for BCA superconductor, it is expected that the Josephson current will be carried by S-wave spin singlet Cooper pair. Now the question is it possible to have this Josephson current mediated by any other kind of pairing? Yes, I will be showing you that even using a BCA superconductor, we can have the Josephson current carried by other type of Cooper pairs. And for that, what we do, like we take a while nodal loop semimetal and we use the surface of this wild nodal loop semi-metal, and we place the two superconductors on the surface. This is actually a cartoon diagram, and this while nodal loop semi-metal is a recently identified topological semi-metals, and this is the minimal model of while nodal loop semi-metal, which essentially captures all the essential physics of while nodal loop semi-metal, and this sigma in the spin basis, and this part is actually the kinetic energy term, and this gives you the spin orbit interaction and the chemical potential as well. And this alpha 1, alpha 2 and mu, and it defines actually the Fermi surface, and I will come back to it a few slides later. And for the superconductor, we use the BGG Hamiltonian, where the superconductivity is induced or introduced using this term, which is basically the S-wave spin singlet term. And this is the normal part Hamiltonian of the superconductor, essentially the parabolic band structure with this chemical potential is mu SC. Yeah, so let us have a look what happens on the surface of wild nodal loop semi-metal. In wild nodal loop semi-metal, actually both the valence and the conduction bands, they cross each other via a circular line. So we have a circular Fermi surface. It can be a torus too. It depends on the two parameters I have mentioned in the previous slides, like alpha 1, alpha 2, and also the chemical potential. But we choose all these parameters in such a way that we have a circular Fermi surface. And this happens in the bulk band structure. There are also some surface states, which all the surface states actually enclosed by a circle, which is nothing but the projection of this nodal loop onto the surface. And interestingly, all the surface states are strongly spin polarized. If it is, and it's strongly spin polarized in the opposite direction at the two opposite surfaces. If it is down spin polarized on the top surface, then on the bottom surface, it's up spin polarized. So we look at the spin density of states as a function of energy. Now we see that there is a strong spin polarization at E equals to 0, and this is the down spin polarization. And similarly for the bottom surface, we have some up spin polarization. And there are several more materials have already been proposed for the wild nodal loop semi-metal, and some of them have already been experimentally realized. So this strong spin polarization actually of the surface states prevents the conventional spin singlet pairing. So in the conventional spin singlet pairing, what we have like up down minus down up, and we have this strong spin polarization, and it makes the actually the incompatible with the superconductivity. Makes this while nodal loop semi-metal completely is actually prohibiting this spin singlet Cooper pair to penetrate or through this on the surface basically. So no, we cannot expect any proximity induced pairing, and thus we cannot expect any Josephson current when we place these two superconductors on the surface of this material. And in literature, actually, there are some examples showing that it can have these wild nodal loop semi-metal can show the bulk superconductivity as well as surface superconductivity. And it actually prohibits the extrinsic superconductivity, so no proximity induced superconductivity. Rather, it actually makes the wild nodal loop semi-metal exceedingly prone to equal spin ordering. So that means we can expect like up or down type of triplet pairing. And since I am considering only this S wave, and this S wave spin triplet pairing has to be odd frequency in nature. So I have mentioned the new something different from the conventional superconductor, that is the odd frequency equal spin triplet pairing. So let me just define very briefly here. So we know that the Cooper pairs, say we have two electrons, the sigma and sigma prime, with the spin sigma and sigma prime. And this is nothing but a correlation between the two fermion correlation. And we can find the superconducting pair amplitude from this anomalous Green's function. So in BCA superconductor, we never consider this time parameter, but this correlation is possible with a time difference in between the two electrons. So if we introduce the time parameter for the two electrons, T1 and T2, and if this correlation function is odd with respect to the interchange of the time of the two electrons, so then we will call it a odd in time or in frequency, equivalently frequency of the two electrons. So that's why we call it a odd frequency Cooper pair. And it allows of the different type of symmetry of the Cooper pair in addition to its this PCS S-wave, that is S-wave spin singlet. We can have, for example, we can have this S-wave spin triplet, we can have P-wave spin singlet, and so on. But here I will be considering only this S-wave spin triplet type. And this concept of odd frequency was first introduced by Berezinski in the year 1974. Later, Palatsky and Abraham introduced this odd frequency concept in the context of superconductivity in the year 1992. So later, let me have a look at how much odd frequency equals spin triplet pairing we have on the surface of wild nodal loop semi-metal. And so for that, we calculate this. I'm showing here the results for the imaginary part of this anomalous Green's function. And it's we can have a similar results for real part of this anomalous Green's function too. Now I am considering here for all the four spin configurations. So this red line corresponds to the up down minus down on, that is the PCS spin singlet, and the rest of the three like up down down or mixed spin triplet, both the equal spin and the mixed spin triplet. And we can see that they are odd in with respect to this omega. The blue one is the down down spin triplet pairing is the dominating one here, and we have also a little bit like spin singlet pair amplitude, and at the same time up and mixed spin triplet is very little bit. And I'm showing the results here for nx equal to 1. So we discretize actually the whole lattice structure along discretize along the x direction. So this nx equal to 1 means the site where the superconductor lead is attached to the wild nodal loop semi-metal surface. And when we move to the inwards, we see that this is relatively towards the inner side of the surface. Now we see that all the three like up, equal spin triplet, mixed spin triplet, and the spin singlet, they die out. We have only this blue one. So this down spin triplet pairing. Yeah.
9 minutes are up. Please go ahead.
Okay. So I'm showing here. So, and also there are some other results we have in the paper. We have shown in the paper. So if you're interested, please have a look. And then the main summary is that so no conventional, that is the S-wave spin singlet pairing here. We have only odd frequency equal spin triplet pairing. And this happens due to the strong spin polarization of the Drummer surface states. And we also check the P wave. So there is no P wave actually. Only we have a S wave, and which is also stable against the disorder. And this setup is experimentally feasible too. So next we calculate the Josephson current, and let's have a look what happens to the Josephson current. So I'm showing here the critical current as a function of the coupling strength. Coupling strength means the coupling between the superconductor and the wild nodal loop surface. And we see that this magenta line, actually the current is increasing and then it saturates for and now, so we see that there is a finite amount of Josephson current, but we cannot expect any, we have seen that there is no S-wave spin singlet pairing penetrating towards into the surface. So we cannot expect any current carried by this spin singlet pairing. So it must be the only odd frequency pairing which is carrying the Josephson current here. Next, we compare the current with the normal metal. What happens if we place a normal metal here, exactly the same setup, there's just only we have this normal in place of this wild nodal loop semi-metal, and we see that the current is suppressed with respect to the normal metal, and this happens due to the flat band nature of the almost flat band nature of the Drummer surface states. And we also, for the confirmation, we calculate the current in the subsurface layer along this Z direction. Now we see that at the site where the superconductor is attached to the surface, the current is decreasing and is highest at the site where this actually the lead is attached. But in the middle, actually, we have almost the similar current. It's actually the spin polarization of the Drummer surface states and also the flat band nature of the Drummer surface states forces the current to flow through the subsurface layers. And for further confirmation, we do some other analysis, which we have presented in our paper. And to finally conclude that, so there profound or frequency pairing that can be generated on the surface of wild nodal loop semi-metal. And we do not need any engineering, because in the literature, there are many examples, or most of the examples to where we have generated this frequency pairing. People have used either non-collinear magnetic layers on spin or spin orbit active interface, but there is no need of any kind of engineering here. This oil nodal loop semi-metal is actually effective than many other prototype examples existing in the literature. And we have finite Josephson current that can be measured, and that's the Josephson current is carried by only or frequency pairing. And we have, as I said, that there are some analytical and as well as some other results. If you're interested, please have a look up our paper. And thanks for your kind attention.
Thank you, Paramita. We are very short on time. Are there any questions? Let me just ask a quick question.
Yeah.
So if this setup that you propose is realized, and if the Josephson current is measured, so a certain critical, so does that serve as evidence for odd frequency pairing?
Actually, it's a indirect detection. So we are calculating the pair amplitude and then showing that, okay, we do not have any SOS mean singlet pairing. It's hard to identify the contribution for odd frequency all the times in any kind of systems. So since here we cannot expect any Josephson current carried by spin singlet, so that's why we are arguing that we have the Josephson current carried by odd frequency triplet pairing here. It's indirect detection, actually.
Yes, I understand. Yeah. Good. Okay. So I see there are no other questions.